Imagine a cosmic ocean, vast and seemingly endless, populated by islands of light we call galaxies. We see these islands, we study their inhabitants, the stars and the swirling clouds of gas and dust. But what if I told you that these shining beacons are just the tip of the iceberg, that they represent a mere fraction of the true mass of the universe, that what we can observe accounts for a paltry few percentage points of what is actually out there? It is a perplexing, almost unbelievable truth. The universe, it seems, is playing hide and seek. For decades, scientists have grappled with a profound enigma. Most of the universe's mass is missing. Not misplaced, not hiding behind some giant cosmic curtain, but fundamentally invisible. We call it dark matter, a name that only deepens the mystery, hinting at something lurking in the shadows, something we cannot directly see, touch, or interact with. At least, not in any way we currently understand. This isn't some minor cosmic accounting error. We are talking about approximately 85% of the universe's total mass. 85%. That means everything we see, from the smallest asteroid to the largest supercluster of galaxies, represents just a sliver of the cosmic pie. The rest? It is a ghost. A phantom presence, felt only through its gravitational influence. How is this possible? How can something so abundant remain so elusive? These are not simple questions, and the answers are not readily apparent. But the implications are staggering. This unseen substance, this dark matter, dictates the very structure and fate of everything we observe. It shapes the galaxies, binds them together in clusters, and orchestrates the grand cosmic dance. Without dark matter, the universe as we know it would simply not exist. Galaxies would fly apart, stars would never have formed, and the cosmos would be a vastly different, far emptier place. Think of it like this. Imagine building a skyscraper out of toothpicks. It might stand for a moment, but without a strong foundation it would quickly collapse. Dark matter provides that invisible foundation, the gravitational scaffolding upon which the entire visible universe is built. So how do we know it is even there? Do we know it? If we cannot see it, how can we be so sure of its existence? This is where the real detective work begins. Astronomers, physicists, and cosmologists have pieced together a compelling case, drawing on a range of observations and theoretical insights. We will be exploring the evidence, from the rotation of galaxies to the bending of light across vast cosmic distances. Each piece of evidence is another clue in this compelling cosmic puzzle. These observations have allowed us to measure the total mass of galaxies and galaxy clusters, consistently showing a mass discrepancy. This means that we keep discovering that there is far more mass present than what stars and gas can account for. Why can't we see it? That is the million-dollar question, or perhaps the multi-billion-dollar question, in this quest to understand the universe. The most likely explanation is that dark matter interacts very weakly with light and other forms of electromagnetic radiation. It does not absorb, reflect, or emit light in any significant way, rendering it effectively invisible to our telescopes. But this lack of interaction is also what makes it so difficult to detect, forcing us to rely on indirect methods to study its properties. The search for dark matter is not just an academic exercise. It is a fundamental quest to understand the very nature of reality. It challenges our understanding of physics, cosmology, and the universe itself. It is a journey into the unknown, a pursuit that could rewrite our textbooks and reshape our understanding of the cosmos. And as we delve deeper into this cosmic mystery, we are forced to confront some truly profound questions. What exactly is dark matter made of? Is it a new type of particle? Does it interact with normal matter in ways we have yet to discover? Or does its existence point to something even more fundamental, a flaw in our understanding of gravity itself? The implications of these questions are staggering, and the answers could change everything. So, we know it's there, this unseen mass. But what does it do? Think of it not just as some nebulous presence, but as the very architecture of the cosmos. Imagine, if you will, the universe as a vast dark ocean. In this ocean, galaxies are not merely floating at random. They are clustered together, arranged in immense structures that span hundreds of millions of light years. These structures, known as the cosmic web, are not random. They are a testament to the underlying influence of dark matter. Now picture a human body. We see the skin, the muscles, the organs, but beneath it all lies the skeleton, the framework that provides shape, support, and allows movement. Dark matter is, in many ways, the skeleton of the universe. It provides the gravitational scaffolding upon which galaxies form and cluster. How? Well, in the early universe, matter wasn't evenly distributed. There were slight density fluctuations, tiny ripples in the cosmic fabric. Normal matter, the stuff we are made of, interacts with light and radiation, which tends to smooth things out. But dark matter, remember, interacts very weakly. It was immune to these smoothing effects. This meant that dark matter clumps grew larger and larger, pulling in more and more material through gravity. These clumps of dark matter became the seeds around which galaxies would eventually form. Normal matter, drawn in by the gravitational pull of these dark matter halos, coalesced to form stars, planets, and eventually galaxies. Without dark matter, those initial density fluctuations would have been too small to form the structures we see today. The universe would have remained a relatively smooth, featureless expanse. It is a truly staggering thought. The galaxies we see, the stars we admire, the planets that might harbor life, all owe their existence to this invisible substance. Dark matter is the master architect, the silent builder, the unseen hand that shaped the cosmos. The scale of this unseen skeleton is almost incomprehensible. We are not talking about a few extra pounds of missing mass. Dark matter outweighs normal matter by a factor of more than 5 to 1. That means for every kilogram of ordinary stuff, protons, neutrons, electrons, there are more than 5 kilograms of this mysterious dark substance. Consider our own Milky Way galaxy. We can see the stars, the gas, the dust all swirling around the galactic center. But if we could somehow visualize the dark matter halo that surrounds our galaxy, it would dwarf the visible disk. It would extend far beyond the luminous edge, a vast invisible sphere of gravitational influence. Understanding this cosmic skeleton is not just about understanding the structure of the universe, it is also about understanding its evolution. Dark matter has played a crucial role in shaping the cosmos from its earliest moments to the present day. And its influence will continue to shape the future of the universe, dictating how galaxies form, how clusters evolve, and ultimately, whether the universe will continue to expand forever or eventually collapse in on itself. The future of the cosmos hinges on the properties of this invisible skeleton. The more we learn about dark matter, the better we can understand the grand cosmic story. The key to unlocking the secrets of the cosmos, it seems, lies hidden in the shadows. The pursuit of unveiling this mystery is the great scientific quest. So we have established the pervasive influence of this cosmic skeleton, this dark matter, shaping the very fabric of the universe. But the road to this understanding was not a straight and easy one. This scientific quest has been filled with twists, turns, and moments of both triumph and frustration. The first whisper of this unseen mass came not from elaborate experiments or deep space probes, but from the meticulous observations of a somewhat eccentric yet undeniably brilliant astronomer. Prepare to journey back to the 1930s, to the mind of Fritz Zwicky, a man who dared to challenge the prevailing view of the cosmos. Zwicky was not your typical astronomer. He was known for his sharp wit, his unconventional ideas, and his sometimes abrasive personality. Born in Bulgaria, he later made his mark at the California Institute of Technology, where he dedicated his life to exploring the universe. He was a true visionary, predicting the existence of neutron stars and developing innovative techniques for studying galaxies long before they became mainstream. But it was his work on galaxy clusters that would ultimately lead him to stumble upon one of the biggest mysteries in modern cosmology. Imagine, if you will, a swarm of galaxies bound together by gravity, orbiting a common center. This is a galaxy cluster, one of the largest structures in the universe. Zwicky focused his attention on the Coma cluster, a sprawling collection of thousands of galaxies located over 300 million light-years away. He meticulously measured the velocities of these galaxies, carefully tracking their movements through space. And that is when he noticed something strange. The galaxies in the Coma cluster were moving far too fast. According to the laws of gravity, they should have been flying apart. The visible mass of the galaxies, the stars, the gas, and the dust simply wasn't enough to hold the cluster together. There had to be something else, something unseen, exerting a gravitational pull that kept the galaxies from escaping. Zwicky calculated just how much extra mass was needed. The answer was astounding. The Coma cluster needed hundreds of times more mass than what could be accounted for by the visible matter. It was as if a vast, invisible hand was holding the cluster together. Now, most scientists would have dismissed this as an anomaly, a measurement error, or perhaps some unknown quirk of gravity. But Zwicky was not one to shy away from bold conclusions. He proposed that there was a substantial amount of unseen mass within the cluster, mass that he couldn't see, but whose gravitational effects were undeniable. He coined the term Dunkel Materie, or dark matter in German, to describe this mysterious substance. Imagine the reaction. Here was this outspoken astronomer challenging the established views of the scientific community. He was suggesting that the universe was filled with this strange, invisible stuff that no one had ever seen before. His ideas were met with skepticism, even ridicule. Most astronomers dismissed Zwicky's findings, suggesting that there must be some other explanation for the high velocities of the galaxies. Perhaps gravity behaved differently on such large scales, or perhaps there were unseen stars or gas clouds lurking in the cluster. Zwicky's initial findings were largely overlooked. He had peered into the void and heard whispers of something unseen, but the scientific community wasn't ready to listen just yet. But even though his contemporaries didn't immediately embrace his ideas, Zwicky's work laid the foundation for future investigations. It was a seed planted in the fertile ground of scientific inquiry, waiting for the right conditions to sprout. His work serves as a reminder that groundbreaking discoveries often face initial resistance. Sometimes the most profound insights come from those who dare to question the status quo, even if their ideas are initially met with skepticism. His contributions were the first clues in uncovering the truth about the universe. It was not until decades later, with the advent of new observational techniques and a growing body of evidence, that the scientific community would begin to fully appreciate the significance of Zwicky's pioneering, albeit controversial, early work. And the story certainly doesn't end here. But while Zwicky had fired the opening shot in this cosmic whodunit, his evidence, gathered in the relative infancy of modern observational astronomy, lacked the precision to truly convince the scientific community. The mystery of the missing mass remained a tantalizing yet largely unproven hypothesis. The astronomical world, it seemed, was waiting for a more decisive clue, a smoking gun that would force everyone to confront the unsettling possibility that what they saw was not all there was. The universe, as it turned out, was about to provide just such a clue, delivered by a determined astronomer and her equally dedicated colleague. Enter Vera Rubin and Kent Ford. The late 1960s and early 1970s were a time of great progress and paradigm shifts, and not just in the realm of rock and roll and bell-bottom jeans. On the cutting edge of astronomy, Vera Rubin, a name that would soon become synonymous with dark matter, was diligently observing the rotation of spiral galaxies. Rubin, an astronomer whose career had faced considerable hurdles due to the prevailing attitudes towards women in science, possessed a fierce determination and an unwavering commitment to uncovering the secrets of the cosmos. She, along with her collaborator Kent Ford, an instrument builder and astronomer, set out to meticulously measure the velocities of stars within these galaxies, using a specialized spectrograph that Ford had painstakingly crafted. Now, imagine a spinning vinyl record. The closer you are to the center, the slower the record spins. Common sense, and the laws of physics would suggest that the same principle should apply to galaxies. Stars closer to the galactic center, where most of the visible mass resides, should orbit faster than stars at the outer edges. But Rubin and Ford discovered something completely unexpected. As they peered at galaxies such as Andromeda and others, the stars at the outskirts were moving far too quickly. In fact, their orbital speeds remained almost constant, even at incredibly large distances from the galactic center. It was as if these stars were defying gravity, as if they were being propelled by some unseen force. Think of it like a carousel, where the horses on the outer rim are somehow keeping pace with those closer to the center, an impossible feat in the real world. These observations were a bombshell. The established laws of physics, based on the distribution of visible matter, simply could not explain these flat rotation curves. Stars on the edge of the galaxy were doing the unthinkable, breaking galactic speed limits, and the implication was profound. It suggested that galaxies were embedded in vast halos of unseen mass, extending far beyond the luminous disk of stars and gas. This unseen mass was exerting a gravitational pull, keeping those outer stars from flying off into intergalactic space. Rubin's meticulous observations, coupled with Ford's instrumental expertise, provided the most compelling evidence yet for the existence of dark matter. Her work brought the dark matter problem firmly into the mainstream of astrophysics. It was no longer a fringe idea, a quirky hypothesis championed by a lone wolf astronomer. Rubin's data was undeniable. Her analysis was rigorous, and her conclusions were inescapable. Galaxies were not what they seemed. They were merely the visible tips of much larger, much more massive structures, dominated by an unseen, unknown substance. A substance that now demanded to be understood. The whispering voices Zwicky had heard decades ago were now amplified into a clear, insistent call. And so, a new era of dark matter research was born, one fueled by the revolutionary work of Vera Rubin and Kent Ford. The quest to unravel the nature of this invisible skeleton of the universe had truly begun, and the mysteries it held promised to reshape our understanding of everything. Vera Rubin's discovery wasn't just an incremental finding, it was a galactic speed trap waiting to be sprung. But what exactly did she find, and why was it so revolutionary? Let's get down to the nitty-gritty of galactic rotation curves and why they became such a powerful piece of evidence in the dark matter puzzle. Imagine you're standing at the edge of a highway watching cars speed by. Common sense tells you that the cars closest to you appear to move faster than the ones further away. This is because your perspective changes with distance. Now, apply that principle to a galaxy. We expect the stars closest to the galactic center, where the visible matter is concentrated, to orbit faster than the stars further out. Why? Because gravity, as we understood it, dictates that the closer you are to a source of mass, the stronger the gravitational pull. More gravitational pull equals higher orbital speed. Think of it like a cosmic figure skating competition. The skaters closest to the center of the rink need to spin faster to stay in their orbit, because the rink itself is pulling them inwards with more force. The skaters further out can spin slower and still maintain their trajectory. This is Newtonian Physics 101. But here is where things get weird. When Vera Rubin meticulously measured the velocities of stars in spiral galaxies, she found that this expectation was completely wrong. Instead of slowing down further out from the galactic center, the stars stubbornly maintained high speeds, almost as if they were all following the same speed limit. It's like those skaters on the outer rim of the rink suddenly discovering they possess the same angular momentum as the ones spinning near the center. It defies the rules of the game. These flat rotation curves, as they became known, were a major problem for our understanding of galaxies. According to the amount of visible matter we could see, the stars at the edge of galaxies should have been slowing down and eventually flying off into intergalactic space. But they weren't. They were maintaining their speed as if something else was holding them in place, exerting an extra gravitational pull. To put it simply, the visible matter in galaxies was not enough to explain the observed rotation speeds. The stars were moving faster than they should have been, given the amount of mass that we could actually see. This discrepancy pointed directly to the presence of a massive, invisible component, something that was exerting a gravitational force but not emitting or absorbing light. This invisible component, of course, is what we now call dark matter. The flat rotation curves provided some of the most compelling and direct evidence for its existence. They suggested that galaxies are surrounded by vast halos of dark matter, extending far beyond the visible disk. These halos act as gravitational anchors, keeping the outer stars from escaping. Visualize this, if you will. Imagine a spiral galaxy as a giant frisbee spinning in space. Now, picture this frisbee surrounded by a much larger, invisible sphere of dark matter. This sphere is so massive that its gravity affects the motion of everything within it, including the stars at the edge of the frisbee. Even though we can't see this sphere, we can infer its presence by observing how it affects the motion of the visible stars. Consider the Andromeda Galaxy, our closest galactic neighbor. Its rotation curve is remarkably flat, extending far beyond the visible edge of the galaxy. This indicates that Andromeda is embedded in a massive halo of dark matter, perhaps 10 times more massive than all the stars and gas combined. Across the observable universe, similar rotation curves are observed in other spiral galaxies, suggesting that dark matter halos are a common feature of galactic structure. From the majestic Sombrero Galaxy, tilted elegantly towards our line of sight, to the Whirlpool Galaxy, locked in a gravitational dance with a smaller companion, the story remains the same. Stars at the edge are behaving as though they are caught in the grip of something unseen. But is this the definitive answer? Does dark matter explain everything? Or are there other possible explanations for these bizarre galactic speed limits? These questions would launch countless research endeavors into the hidden face of our reality. But if these galactic speed limits are being broken, how do we really know just how much mass is truly out there? Is it simply a matter of adding up the stars like counting sheep? The reality, as you might suspect, is far more intricate. Astronomers have developed a fascinating arsenal of techniques to weigh the unseen, to get a handle on the total mass of galaxies and clusters of galaxies, and what they consistently find only deepens the mystery of dark matter. One of the most powerful methods relies on the very same principle that revealed the dark matter in the first place: the motion of galaxies within clusters. Imagine a cosmic ballet where hundreds or even thousands of galaxies are swirling around each other, locked in a gravitational dance. By carefully measuring the velocities of these galaxies, how fast they are moving towards or away from us, astronomers can infer the total mass of the cluster. It's like trying to determine the weight of a hidden object by observing how it affects the movement of other objects around it. Think of it as a cosmic tug of war. The faster the galaxies are moving, the stronger the gravitational pull must be to keep them from flying apart. By applying Newton's laws of gravity, scientists can calculate the total mass required to hold the cluster together, and time after time, this calculation reveals a staggering discrepancy. The mass needed to explain the observed velocities is far greater than the mass of all the visible stars, gas, and dust combined. In some cases, the discrepancy is a factor of 10, 50, even 100. That means 9/10 or 99/100 of the mass is missing, hidden from our view. But the galactic ballet isn't the only way to weigh the unseen. Another crucial technique involves studying the temperature of hot gas trapped within galaxy clusters. These clusters are not just collections of galaxies. They are also filled with vast clouds of superheated gas, so hot that it emits X-rays. This gas is trapped within the cluster's gravitational field like air in a balloon. The hotter the gas, the faster its particles are moving, and the stronger the gravitational field must be to keep the gas from escaping. By measuring the temperature of the X-ray emitting gas, astronomers can infer the strength of the gravitational field, and therefore the total mass of the cluster. And once again, the results are consistent. The total mass inferred from the gas temperature is far greater than the mass of the visible matter. This is yet another independent confirmation of the mass discrepancy, another piece of evidence pointing to the existence of dark matter. It is like taking the temperature of a giant cosmic oven. The higher the temperature, the more energy is needed to keep the oven hot. In this case, the energy comes from the gravitational pull of the cluster. By measuring the temperature of the oven, we can figure out how much gravitational pull is present, and that tells us how much mass is in the cluster. Let's consider the Abell 2218 cluster, a colossal collection of galaxies located over 2.7 billion light-years away. Observations of the hot gas within this cluster reveal a temperature of nearly 100 million degrees Celsius. That's hot enough to melt almost any known substance. The amount of mass needed to keep this gas from escaping is enormous, far greater than the combined mass of all the galaxies in the cluster. What is holding it all together? You guessed it. Dark matter. So, what does all this mean? Well, it means that we have multiple independent ways of measuring the total mass of galaxies and clusters of galaxies, and all of these methods consistently point to the same conclusion. There is far more mass out there than what we can see. The visible mass budget, the sum of all the stars, gas, and dust, simply doesn't add up. It's like trying to balance your checkbook only to discover that you are missing a significant amount of money. But how significant are we talking? Consider a typical spiral galaxy like our own Milky Way. The visible mass of the Milky Way is estimated to be around 200 billion times the mass of the Sun. That's a lot of stars. But the total mass of the Milky Way, including dark matter, is estimated to be 10 times higher, somewhere around 2 trillion solar masses. That means the visible matter accounts for only 10/100ths of the galaxy's total mass. The remaining 90/100ths is dark matter, an invisible halo surrounding the galaxy, exerting a gravitational pull that shapes its structure and influences its evolution. Across the cosmos, the story is the same. Galaxies are embedded in vast halos of dark matter, and clusters of galaxies are held together by an even greater amount of this unseen substance. It is as if the universe is playing a cosmic trick on us, showing us only a fraction of what is actually there. It is as though we are seeing a fleet of icebergs on the ocean, and the only visible part of these icebergs is the tip above the water. The vast majority of the iceberg is hidden beneath the surface, just like dark matter is hidden from our telescopes. So, how do we penetrate the surface? How do we get a glimpse of this hidden mass? The answer, as we will see, lies in the bending of light across vast cosmic distances. But how do you observe something that doesn't emit, absorb, or reflect light? It sounds like an impossible task, akin to trying to photograph a ghost. Yet the universe, in its infinite complexity, has provided us with a clever workaround, a cosmic cheat code, if you will. What if I told you that gravity itself can act as a lens, bending and distorting light from distant objects, revealing the presence of unseen mass along the way? This is the phenomenon known as gravitational lensing, and it's one of the most powerful tools we have for mapping the distribution of dark matter in the cosmos. Imagine a powerful magnifying glass. When you hold it up to a page, it bends the light rays, making the letters appear larger and distorted. Now, imagine a galaxy cluster, an immense collection of galaxies and dark matter sitting between us and a distant quasar, a supermassive black hole actively devouring matter. The cluster's immense gravity warps the very fabric of space-time around it, like a bowling ball placed on a trampoline. As the light from the distant quasar travels towards us, it has to navigate this warped space-time. The gravity of the cluster acts as a cosmic lens, bending the light rays and distorting the image of the quasar. These distortions can take many forms. Sometimes, the light is stretched into long arcs, creating what are known as Einstein rings, named after the man who first predicted this phenomenon. Other times, the light is split into multiple images, creating a bizarre hall of mirrors effect. And in some cases, the distortions are subtle, barely perceptible, but still detectable with sophisticated telescopes and analysis techniques. Think of it as a cosmic funhouse mirror. The massive galaxy cluster acts like a warped mirror, distorting the images of objects behind it. By studying the shapes and orientations of these distorted images, astronomers can reconstruct the shape of the lens, the distribution of mass within the cluster. And because dark matter makes up the bulk of the mass in these clusters, gravitational lensing allows us to map its distribution, revealing the hidden architecture of the universe. The beauty of gravitational lensing is that it doesn't rely on detecting light from the dark matter itself. Instead, it relies on the fact that dark matter has gravity, and gravity bends light. It's like using the shadow of an object to determine its shape, even if you can't see the object directly. There are two main types of gravitational lensing: strong lensing and weak lensing. Strong lensing is what happens when the light from a background object is significantly distorted, creating dramatic arcs, rings, and multiple images. These are the most visually striking examples of gravitational lensing, and they provide valuable information about the mass distribution in the lensing object. Weak lensing, on the other hand, is more subtle. It involves the minute distortions of countless background galaxies caused by the gravity of intervening dark matter. Individually, these distortions are almost imperceptible, but when analyzed statistically over large areas of the sky, they reveal the underlying distribution of dark matter. It's like trying to detect the ripples on a pond by looking at the reflections of the trees on the shore. Each ripple is tiny, but by analyzing the patterns of the reflections, you can infer the presence of the ripples and map their distribution. One of the most spectacular examples of gravitational lensing is the Abell 1689 cluster, located over 2 billion light-years away. This cluster is so massive that it acts as a powerful lens, distorting the images of hundreds of background galaxies into elongated arcs. By studying these arcs, astronomers have been able to create a detailed map of the dark matter distribution in the cluster, revealing a complex network of filaments and clumps. These maps confirm that dark matter is not evenly distributed throughout the universe. Instead, it forms a vast, interconnected web with galaxies and clusters of galaxies located at the nodes of this web. It is as if the visible universe is draped over an invisible scaffolding of dark matter, a testament to its fundamental role in shaping the cosmos. But gravitational lensing is not just a tool for mapping dark matter, it is also a powerful probe of the distant universe. By bending the light from faraway galaxies, gravitational lenses can magnify their images, allowing us to see them in greater detail than would otherwise be possible. It's like having a giant cosmic telescope at our disposal, allowing us to peer deeper into the universe and study the formation and evolution of galaxies in the early universe. So the next time you look up at the night sky, remember that the light you see has traveled billions of light years, been bent and distorted by the gravity of unseen matter, and ultimately revealed the hidden architecture of the cosmos. The universe is full of surprises, and gravitational lensing is just one example of how we can unlock its secrets by thinking outside the box. The universe continues to surprise us, but what other secrets are there, and how can we see them? Gravitational lensing gives us a peek at the hidden skeleton of the universe, but what if we could travel back in time, not physically, of course, but through the looking glass of scientific observation, to witness the universe in its infancy? What if we could see the very first light emitted after the Big Bang, a faint echo of creation itself? It sounds like something out of science fiction, but astronomers have done just that. They have captured the cosmic microwave background, or CMB, the faint afterglow of the Big Bang, and within it they have found crucial clues about the composition of the early universe, including the elusive dark matter. Imagine the universe as a newborn baby, just 380,000 years old. In cosmic terms, that's practically yesterday. At this point, the universe was a hot, dense plasma, a swirling soup of photons, electrons, and atomic nuclei. Light and matter were constantly interacting, creating a cosmic fog that obscured everything. But as the universe expanded and cooled, this fog began to clear. Electrons and nuclei combined to form neutral atoms, allowing photons to travel freely through space for the first time. This is the moment when the CMB was born, the oldest light in the universe, a snapshot of the cosmos at its earliest stage. Now this afterglow isn't uniform. It is filled with tiny temperature fluctuations, variations of only a few parts per 100,000. These fluctuations may seem insignificant, but they are actually the imprints of primordial density variations, the seeds from which all the structures in the universe would eventually grow. Think of it as a cosmic blueprint, etched onto the fabric of space-time, revealing the underlying architecture of the cosmos. How do these tiny temperature variations relate to dark matter? Well, remember that in the early universe, dark matter, normal matter, and radiation were all interacting. The interplay of these three components shaped the pattern of fluctuations in the CMB. Normal matter, the stuff we are made of, interacts with light and radiation, which tends to smooth out density variations. But dark matter, as we know, interacts very weakly with light. This means that it was able to clump together more easily, creating gravitational wells that attracted normal matter. The specific pattern of these fluctuations, the size and distribution of the hot and cold spots in the CMB, is extremely sensitive to the amount of dark matter in the universe. By carefully analyzing this pattern, astronomers can determine the precise amount of dark matter that was present in the early universe. It's like analyzing the sound of a bell. The specific pattern of overtones and harmonics reveals the material the bell is made from and how it was shaped. In this case, the sound of the universe reveals its composition. The results of these analyses are nothing short of remarkable. The pattern of fluctuations in the CMB strongly supports the existence and quantity of dark matter predicted by cosmological models. In fact, the CMB provides some of the most precise measurements of the dark matter density in the universe. It is like having a cosmic ruler, allowing us to measure the amount of dark matter with unprecedented accuracy. These fluctuations, they whisper secrets from a time when the universe was barely a toddler. These findings offer very strong support for the idea of a universe where dark matter dominates. And the most amazing part is that this confirmation comes from the universe when it was only 380,000 years old. Imagine that everything that would ever exist was just a tiny cloud, and that the CMB is the first photograph ever taken. This evidence from the CMB is so compelling that it has become a cornerstone of modern cosmology. It has helped to solidify our understanding of the Big Bang theory, the formation of large-scale structures in the universe, and the role of dark matter in shaping the cosmos. It's like finding the missing piece of a cosmic puzzle, completing the picture of the early universe. But that wasn't all of the knowledge that scientists uncovered, and they continued to peer through the lens to see into the very, very beginning. What if we could view this primordial light on a collision course? What if we could see these theories in motion? So we have peered into the afterglow of creation, witnessing the universe as an infant, only 380,000 years young. We've analyzed the cosmic microwave background, finding compelling evidence for the existence of dark matter, etched into the very fabric of space-time. But what if we could fast forward billions of years to see how this dark matter has shaped the universe we observe today? What if we could witness the grand cosmic architecture, the vast network of galaxies, clusters, and voids that spans the observable cosmos? Prepare to witness the formation of the cosmic web, the largest structure known to exist, and to understand the critical role dark matter played in its creation. Imagine a spider's web, but on a scale that dwarfs even our most audacious imaginings. Extend that web to span billions of light years, with individual strands thicker than galaxies, and nodes holding clusters of thousands of galaxies. That is the cosmic web, a vast, interconnected network of matter that forms the large-scale structure of the universe. It's a tapestry woven by gravity, a celestial masterpiece sculpted by the unseen hand of dark matter. But how did this web form? In the early universe, matter wasn't distributed evenly. There were tiny density fluctuations, slight variations in the concentration of matter. These fluctuations, amplified by the relentless pull of gravity, grew over time. Normal matter, influenced by radiation and pressure, struggled to clump together effectively. But dark matter, aloof and largely unaffected by these forces, was free to collapse under its own weight, creating gravitational wells that attracted normal matter like moths to a flame. These dark matter concentrations acted as seeds, gravitational anchors around which galaxies and clusters of galaxies would eventually form. They are the hidden supports of the cosmic edifice. Without these gravitational seeds provided by dark matter, the structures we observe today would simply not exist. The universe would have remained a relatively smooth, featureless expanse, a cosmic soup lacking the rich and complex structures we see all around us. To truly appreciate the role of dark matter in forming the cosmic web, we must turn to computer simulations. These simulations, powered by some of the world's most powerful supercomputers, model the evolution of the universe from its earliest moments to the present day. They incorporate all the known laws of physics, including gravity, electromagnetism, and the interactions of subatomic particles, and crucially, they include dark matter. What the simulations show is nothing short of astonishing. When dark matter is included, the simulations accurately reproduce the large-scale structure of the universe, the network of filaments, clusters, and voids that we observe with our telescopes. Galaxies form along the filaments, drawn together by the gravity of the underlying dark matter scaffolding. Clusters of galaxies form at the intersections of these filaments, where the gravitational pull is strongest. And vast voids, empty regions of space almost devoid of matter, emerge between the filaments. But what happens when dark matter is removed from the simulations? The result is a disaster. Without the gravitational influence of dark matter, the structures we observe today simply don't have time to form. The universe remains relatively smooth, lacking the rich complexity of the cosmic web. Galaxies fail to cluster together effectively, and the vast voids never emerge. It is like trying to build a house of cards without a table. The cards might stand for a moment, but without a solid foundation, they will quickly collapse. Dark matter provides that foundation, the gravitational scaffolding that supports the entire visible universe. The simulations reveal a remarkable truth. Dark matter is not just some minor component of the universe. It is the dominant force shaping its structure, the unseen architect of the cosmos. We can compare these simulations to actual observations of the galaxy distribution obtained from surveys like the Sloan Digital Sky Survey, one of the most ambitious and comprehensive astronomical surveys ever undertaken. These surveys have mapped the positions of millions of galaxies, providing us with a detailed picture of the large-scale structure of the universe. When we compare the simulated distribution of galaxies to the observed distribution, the agreement is striking. The simulations accurately reproduce the network of filaments, clusters, and voids that we see in the real universe. This agreement provides strong evidence that our understanding of dark matter and its role in structure formation is on the right track. The simulations provide the blueprint, and the observations show the finished product. Consider the constellation Coma Berenices, a region of the sky relatively devoid of bright stars. Through powerful telescopes, however, we can see that this seemingly empty patch of sky is teeming with distant galaxies, arranged in a vast filament that stretches for hundreds of millions of light years. This filament is just one thread in the vast cosmic web, a testament to the underlying influence of dark matter. So the cosmic web is not just a theoretical construct. It is a real, observable structure, a testament to the power of gravity and the crucial role of dark matter in shaping the universe. It's a reminder that what we see is only a fraction of the story, that the universe is far more complex and mysterious than we can ever fully comprehend. But while the cosmic web offers compelling evidence for the existence of dark matter, it also presents new challenges. How did these vast structures form in such detail? What are the precise properties of dark matter that allowed it to shape the cosmos in this way? These are questions that continue to drive research in cosmology and particle physics. The answers will undoubtedly lead to new discoveries and a deeper understanding of the universe. But it's not just about the large-scale structures. What if we could zoom in and witness something so spectacular that it would reinforce all the evidence we already have? What if we could see dark matter at work, not just in simulations or maps, but in a real-life, cosmic collision of unimaginable scale? So, we have witnessed the formation of the cosmic web, this vast scaffolding upon which the visible universe is built. But what if we could see dark matter in action, not just in simulations or maps, but in a real-world, cosmic event of unimaginable scale? What if we could observe a collision so cataclysmic, so energetic, that it would offer undeniable proof of dark matter's existence, almost like a cosmic photograph capturing it in the very act of shaping reality? Prepare to witness the bullet cluster, a collision course that has become one of the most direct and visually compelling pieces of evidence for dark matter. Imagine two massive galaxy clusters, each containing hundreds of galaxies, trillions of stars, and vast clouds of superheated gas hurtling through space towards each other at millions of miles per hour. This isn't some gentle cosmic dance. This is a head-on collision, a cataclysmic event that unfolds over millions of years, reshaping the very fabric of space-time. These are not just galaxies bumping into each other. This is akin to two cosmic freight trains colliding at full speed. As these clusters collide, the galaxies themselves, spread so far apart, largely pass through each other unscathed, like bullets through smoke. But the hot, X-ray emitting gas, which makes up most of the normal matter in the clusters, experiences something quite different. As the gas clouds collide, they generate immense friction, slowing down dramatically and creating a shockwave much like the sonic boom from a supersonic jet. This heated gas lags behind the galaxies, forming a distinct bright cloud that is easily visible to X-ray telescopes. This is where the story gets truly interesting. Astronomers using gravitational lensing were able to map the distribution of mass in the bullet cluster. What they found was astonishing. The bulk of the mass, the region with the strongest gravitational lensing effect, was not located where the hot gas was. Instead, it had passed right through the collision, continuing on its trajectory, seemingly unaffected by the interaction. It's like the engine of the train continuing forward while the boxcars are stopped behind, piled in a heap. This separation of normal matter, the hot gas, from the gravitational mass is a smoking gun, a clear indication that most of the mass in the bullet cluster is not in the form of ordinary matter. It's something else. Something that interacts very weakly with itself and with normal matter, allowing it to pass through the collision unimpeded. That something, of course, is dark matter. Imagine that you have two snow globes filled with sand and rocks. You smash these snow globes together. The sand, representing the normal matter, would slow down and be scattered all over the place. The rocks, representing the dark matter, would largely pass through each other, continuing on their original trajectories. The bullet cluster presents a significant challenge to modified gravity theories, alternative explanations that attempt to explain the observed gravitational effects without invoking dark matter. These theories often struggle to explain the separation of mass and light observed in the bullet cluster. The bullet cluster is so named because of the distinct bullet shape of the hot gas in one of the colliding clusters. This bullet shape is created by the shock wave generated as the gas plows through the other cluster. It is a visual reminder of the incredible forces at play in this cosmic collision. It is like a cosmic crime scene, with the evidence scattered across millions of light years. The slow-moving gas, the unimpeded dark matter, the distorted images of background galaxies, all tell the same story. Dark matter is real, and it plays a dominant role in the structure and evolution of the universe. But what does this cosmic collision really tell us? The bullet cluster provides compelling evidence that dark matter is not just some theoretical construct, but a real physical substance that interacts primarily through gravity. It demonstrates that dark matter can separate from normal matter during a collision, reinforcing the idea that it is composed of particles that interact very weakly with each other and with ordinary matter. However, the bullet cluster is just one piece of the puzzle. It leaves a myriad of questions unanswered. What exactly is this mysterious substance that makes up most of the universe's mass? What are its properties? How can we detect it directly? And what does its existence tell us about the fundamental laws of physics? What other evidence will we find that either supports or refutes these findings? The bullet cluster, a spectacular collision, a visual testament to the existence of something beyond our everyday experience. But what if I told you that this unseen mass isn't just some exotic, undiscovered particle? What if I told you that it cannot be the same stuff that makes up you, me, the stars, the planets, everything we can see and touch? That is the challenge now, to eliminate the suspects, to delve into what dark matter isn't. Consider the matter we know, the protons, neutrons, and electrons that form atoms, the building blocks of everything familiar. We call this baryonic matter. Could the missing mass simply be ordinary matter hiding in the shadows, perhaps as countless rogue planets drifting in the void or colossal black holes lurking unseen? It is a natural question to ask. After all, the universe is vast, and there are plenty of places where ordinary matter could potentially hide. Could it be vast clouds of gas and dust so cold they are invisible to our telescopes? Perhaps countless dim stars, brown dwarfs too faint to be seen across such cosmic distances? The answer, surprisingly, is no. While such objects certainly exist, they simply cannot account for the sheer amount of missing mass. There is a cosmic accounting principle at play, a constraint imposed by the very birth of the universe itself. This principle is called Big Bang nucleosynthesis, a rather daunting term for a profoundly elegant process. In the first few minutes after the Big Bang, the universe was hot enough and dense enough for nuclear reactions to occur, forging the first light elements: hydrogen, helium, and trace amounts of lithium. The precise abundance of these elements depends critically on the amount of ordinary matter present at that time. It is a delicate cosmic recipe where the slightest change in ingredients yields a drastically different outcome. Astronomers have painstakingly measured the abundance of these light elements in the universe, looking at pristine clouds of gas that have remained relatively unchanged since the Big Bang. These measurements provide a very precise constraint on the total amount of baryonic matter in the universe. The verdict? There is simply not enough ordinary matter to account for the missing mass. Even if we crammed every last proton, neutron, and electron into the darkest corners of the cosmos, it still would not be enough. The universe is stubbornly short on normal stuff. Imagine baking a cake and you know precisely how much flour, sugar, and eggs should go into it to get the perfect consistency and flavor. Now, imagine you find that you are short on flour. You might try to compensate by adding more sugar or eggs, but you will never be able to replicate the original recipe. The abundance of light elements in the universe is like that recipe, setting a strict limit on the amount of baryonic matter that can be present. Furthermore, extensive searches for these hidden reservoirs of ordinary matter have come up short. Astronomers have scoured the skies for dark clouds of gas using radio telescopes and infrared cameras, but they have not found nearly enough to solve the problem. It's like searching for a hidden treasure only to find that the chest is mostly empty. What about those countless rogue planets? Those cold, dark worlds drifting through interstellar space? Microlensing surveys, techniques that search for the subtle brightening of distant stars as a massive object passes in front of them, have placed stringent limits on the number of these objects. While they certainly exist, they are not nearly abundant enough to account for the missing mass. So, we have eliminated ordinary matter as a viable candidate for dark matter. It simply doesn't add up. The universe demands something more exotic, something beyond our everyday experience. But if it is not protons, neutrons, and electrons, what is it? That is the question that now occupies the minds of scientists around the world. The nature of dark matter, it seems, requires something extraordinary, something that challenges our current understanding of the fundamental building blocks of reality. It is a mystery that continues to push the boundaries of physics and astronomy, a tantalizing enigma that promises to reveal new secrets about the universe. So, we have arrived at a cosmic dead end. Ordinary matter, the stuff we know and love, protons, neutrons, electrons, just isn't cutting it as a candidate for dark matter. But what if the answer lies not in some undiscovered particle, but in objects we already know exist, albeit in a form that is exceptionally difficult to detect? What if the universe is simply teeming with a hidden population of dim stars, brown dwarfs, neutron stars, or even black holes? A vast menagerie of cosmic leftovers, too faint to be seen individually but collectively adding up to the missing mass? This idea, while seemingly straightforward, gave rise to the concept of massive astrophysical compact halo objects, or MACHOs for short. The name itself conjures up images of shadowy behemoths lurking in the galactic halo. These objects, faint and compact, could be sprinkled throughout the galaxy, contributing to the overall mass without emitting significant light. It was an appealing prospect, a way to explain the dark matter mystery without invoking any new physics. Imagine a galactic game of hide-and-seek where the players are not elementary particles but entire stars and black holes lurking in the dark corners of space. These machos, these cosmic ninjas, could be silently orbiting the galaxy, their gravitational pull subtly influencing the motion of visible stars. It was an elegant theory, one that resonated with the scientific community. But how do you find something that is designed to be invisible? How do you detect these dim and compact objects lurking in the vastness of space? The answer, as it often does in astronomy, lies in bending light. In this case, the phenomenon of gravitational microlensing. Remember how massive objects can warp space-time, bending the light from objects behind them? Microlensing takes this concept to the extreme. When a massive compact object, a macho, passes directly in front of a distant star, its gravity acts as a tiny lens, magnifying the star's light for a brief period. It's like a cosmic spotlight briefly illuminating a distant object. The amount of brightening depends on the mass of the macho, and the duration of the event depends on its velocity. Astronomers launched ambitious microlensing surveys pointing their telescopes towards the Magellanic Clouds, 2 dwarf galaxies orbiting our own Milky Way. The idea was simple: monitor millions of stars in the Magellanic Clouds and watch for any sudden brightenings that could be caused by machos passing in front. Think of it as a cosmic searchlight scanning the heavens for any telltale flicker, any hint of a hidden object passing in front of a distant star. It was a painstaking process requiring years of observations and sophisticated data analysis, but the potential reward was immense: the discovery of the elusive dark matter. The results, however, were not what the researchers had hoped for. While some microlensing events were detected, the number was far too low to account for the bulk of the dark matter. The search for machos, it seemed, was coming up short. It's like searching for lost coins in a darkened room. You might find a few, but not nearly enough to replace the missing fortune. Microlensing surveys ruled out machos as the primary component of dark matter. These objects, while they certainly exist, are simply not numerous enough to explain the observed gravitational effects. Imagine the disappointment, the realization that this seemingly promising avenue had led to a dead end. The dark matter mystery remained unsolved, the invisible skeleton of the universe still shrouded in darkness. But the search for machos was not entirely in vain. It taught us valuable lessons about the distribution of matter in the galactic halo, and it honed our observational techniques. The quest for machos, though ultimately unsuccessful, served to highlight the need for a more exotic solution. It forced scientists to consider the possibility that dark matter is not made of ordinary objects, but of something entirely new and unexpected. Perhaps dark matter is composed of elementary particles that interact very weakly with ordinary matter. Maybe it is a particle that we have not yet discovered, something that lies beyond the standard model of particle physics. The failure of the macho hypothesis was a turning point, a moment of realization that the answer to the dark matter mystery might lie in the realm of the truly bizarre. The universe, it seemed, was not going to give up its secrets easily. And so the search for the more exotic began, one that would push the boundaries of physics and astronomy to their very limits. The stage was set for a new cast of characters, particles with names like WIMPs and axions, poised to take center stage in this cosmic drama. The quest to profile the elusive dark matter particle was about to begin. We are left with a rather unnerving predicament. Ordinary matter is out. Massive compact halo objects are out. The universe, it seems, is demanding something far more exotic, something that resides beyond the realm of our current understanding. But if it is not made of the familiar, of what stuff is this phantom universe constructed? Can we even begin to describe something we cannot see, touch, or directly interact with? The answer, surprisingly, is yes. Though shrouded in darkness, dark matter does leave clues, faint whispers that allow scientists to piece together a profile of this elusive substance. It's like trying to understand a ghost by studying the objects it moves, the cold spots it leaves behind. What then are the defining characteristics of the dominant dark matter component? What properties must it possess to explain the cosmic phenomena we observe? The first and perhaps most fundamental property is that it must be non-baryonic. That is a rather technical term, but what it means is quite simple. It cannot be made of protons, neutrons, or electrons, the stuff that makes up ordinary matter. We already established why. Big Bang nucleosynthesis places a strict limit on the amount of baryonic matter in the universe, and it simply is not enough to account for the missing mass. So, dark matter must be composed of something else, something entirely new, something that exists beyond the standard model of particle physics. It is the first crucial detail for our cosmic phantom. Next, dark matter must be stable, or at least extremely long-lived. The dark matter that exists today must have been around for billions of years, since the early universe. If dark matter particles were unstable and decayed quickly, they would have long since disappeared, leaving no trace of their gravitational influence. So we are looking for particles that are either completely stable or have lifetimes that are far longer than the current age of the universe. Perhaps the most obvious property of dark matter is that it must interact very weakly with normal matter and light. After all, we cannot see it. It does not absorb, reflect, or emit light in any significant way. This lack of interaction is what makes it so difficult to detect, forcing us to rely on indirect methods to study its properties. But it also provides a crucial clue about its nature. Dark matter particles must be incredibly shy, almost completely indifferent to the world around them. This is not to say that dark matter does not interact at all. It must interact through gravity, otherwise it would not be able to shape the large-scale structure of the universe, to hold galaxies together, and to bend light through gravitational lensing. Gravity is the universal force, the one that affects everything, regardless of its composition or properties. So, dark matter must feel the pull of gravity, and in turn exert its own gravitational influence on the surrounding universe. Think of it as a cosmic puppeteer pulling the strings of gravity to orchestrate the grand dance of galaxies. Another crucial characteristic is that dark matter must be what scientists call cold. This is another slightly technical term, but what it means is that dark matter particles must have been moving slowly in the early universe. This is important for the formation of structure. If dark matter particles were moving too fast, they would have smoothed out density variations, preventing the formation of small-scale structures like galaxies. Cold dark matter, on the other hand, allows small structures to form first, which then merge together to form larger structures, a process known as hierarchical structure formation. Imagine two pools of water, one freezing into solid ice and the other boiling on a hot surface. The frozen ice, the cold one, forms smaller ice fragments allowing for larger and more detailed structures to form more easily, while the boiling water, although still liquid, cannot settle to create anything. So, to recap, our profile of dark matter is starting to take shape. It is non-baryonic, stable, interacts very weakly with normal matter and light, interacts primarily through gravity, and is cold, meaning it was moving slowly in the early universe. These properties provide crucial guidance in the search for dark matter particles. They narrow down the field of candidates, allowing scientists to focus their efforts on the most promising possibilities. It's like having a detailed description of a wanted criminal, allowing the police to focus their search on specific individuals. But what are these particles? What exotic beasts might lurk in the shadows, unseen and unknown? Are they massive and sluggish, barely interacting with the world around them? Or are they light and nimble, flitting through the cosmos like cosmic butterflies? The answers, as we will see, lie in the realm of particle physics, in theories that attempt to unify all the forces of nature, and in experiments that push the boundaries of our technological capabilities. The search for the identity of dark matter is a quest that will challenge our understanding of the universe and perhaps even rewrite the laws of physics. The stage is set for a new era of exploration, an era where we attempt to capture not a criminal, but a cosmic phantom, a force that shapes the destiny of the universe itself. It is now a question of where to look and what to believe as we chase the shadows to the deepest corners of the earth and the edges of our understanding. So we've painstakingly assembled this profile of the universe's dominant yet invisible constituent, non-baryonic, stable, feebly interacting, gravity-driven, and cold. A cosmic phantom indeed. But does this laundry list of properties actually point to a real, tangible particle? Or are we chasing shadows, constructing a phantom based on incomplete information? What if I told you that one of the leading candidates for dark matter not only fits this profile almost perfectly, but also arises naturally from theories seeking to solve other deep puzzles in physics? Get ready to meet the WIMP, the weakly interacting massive particle, the historical frontrunner in the race to identify dark matter. Imagine the world of particle physics, a realm of infinitesimally small particles governed by forces beyond our everyday experience. For decades, physicists have been striving to create a unified theory, a single framework that can explain all the fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. One of the most promising approaches to unification is a theory known as supersymmetry. Supersymmetry posits that every known particle has a heavier partner particle, a superpartner, that we have yet to discover. It is a bit like saying that for every instrument in the orchestra, there is a shadow instrument with a different tone. Now, these superpartners, if they exist, would be massive, and many of them would also be stable. And here is where the magic happens. The lightest supersymmetric particle, often dubbed the neutralino, is predicted to be electrically neutral and interact only through the weak force and gravity. Sound familiar? It is almost as if supersymmetry was designed to produce a perfect dark matter candidate. The neutralino, a WIMP, ticks all the boxes on our dark matter profile, but the appeal of WIMPs extends beyond their compatibility with supersymmetry. There is something almost miraculous about their predicted abundance in the universe. The WIMP miracle, as it has come to be known, refers to the fact that particles interacting through the weak force with masses around 100 times that of the proton would naturally have the right abundance to account for the observed dark matter density. Let me explain how this works. In the early universe, when temperatures were incredibly high, WIMPs would have been constantly created and destroyed in thermal equilibrium with other particles. As the universe expanded and cooled, the production of WIMPs would have slowed down. Eventually, the rate of WIMP annihilation, where two WIMPs collide and destroy each other, would have become too slow to keep up with the expansion of the universe. At this point, the WIMPs would have effectively frozen out, their abundance fixed at a certain level. The remarkable thing is that this freeze-out abundance depends almost solely on the strength of the weak interaction and the mass of the WIMP. Calculations show that for a particle interacting through the weak force, with a mass in the range predicted by supersymmetry, the resulting abundance is almost exactly what is needed to explain dark matter. It is as if the universe has a built-in mechanism to produce just the right amount of dark matter. It's a cosmic coincidence, a numerical alignment that has captivated physicists for decades. It is like discovering that a complex equation designed to solve a completely different problem unexpectedly yields the precise value of pi. This WIMP miracle is what propelled WIMPs to the forefront of dark matter research. The theoretical motivation was strong, the properties aligned perfectly with observations, and the predicted abundance was almost too good to be true. For decades, WIMPs became the leading paradigm, the standard model of dark matter. The expected weak interaction also offers a tantalizing handle for direct detection. If dark matter particles are constantly streaming through our galaxy, then occasionally, just occasionally, they should collide with ordinary matter. A WIMP passing through Earth, for instance, might strike the nucleus of an atom in a detector. The challenge, of course, lies in detecting such a rare and feeble interaction. Think about it. These particles would be incredibly difficult to detect, only interacting weakly. They could pass through light years of normal matter without even noticing it. The predicted properties of WIMPs have fueled an intense experimental effort to detect them directly. Scientists have built elaborate detectors, shielded from all other forms of radiation, hoping to catch a glimpse of a WIMP colliding with an atom. Will these detectors succeed, confirming the WIMP hypothesis and ushering in a new era of particle physics? Or will the elusive dark matter continue to evade our grasp, forcing us to rethink our assumptions and explore alternative possibilities? But what if the key to unlocking the secrets of dark matter lies not in brute force detection of massive particles, but in the ethereal whisper of something almost impossibly light? What if, instead of a heavyweight boxer, we need to find a cosmic feather, a particle so elusive that it barely interacts with anything at all? Prepare to enter the strange and fascinating world of the axion, a dark matter candidate that is as intriguing as it is baffling. Why would scientists even consider such a wispy particle as a solution to the dark matter mystery? The answer, as with so many things in physics, lies in a problem. A very specific, very thorny problem within the standard model of particle physics, known as the strong CP problem. Now, without getting too deep into the quantum mechanical weeds, the strong CP problem basically asks, why is the strong nuclear force, the force that binds protons and neutrons together in the nucleus of an atom, so symmetrical? Why doesn't it violate something called charge parity symmetry, or CP symmetry, in the way that the weak force does? The standard model, in its original form, predicted that the strong force should violate CP symmetry to some degree, but experiments have shown, time and again, that it doesn't. It's as if nature is whispering, "There's something missing here." And this missing piece, this puzzle, is where the axion comes in. Back in the 1970s, physicists Roberto Peccei and Helen Quinn proposed a brilliant solution to the strong CP problem. They suggested that there was a new symmetry in nature, a symmetry that would force the strong force to be CP symmetric. But this symmetry came with a price, a new particle, the axion. Now, axions, if they exist, would be incredibly light, perhaps 1 billion times lighter than an electron. They would also interact extremely weakly with ordinary matter, making them incredibly difficult to detect. But here's the twist. The very properties that make axions so difficult to detect also make them excellent dark matter candidates. Think of it like this. Imagine a room filled with bowling balls, representing WIMPs. Now, imagine a single feather floating through that room, representing an axion. Which is easier to detect? The bowling balls, of course. But what if there were trillions upon trillions of these feathers, so many that their combined weight outweighed all the bowling balls. Suddenly, those feathers become a force to be reckoned with. Axions, according to some theories, could have been produced in vast quantities in the early universe. Their tiny mass, combined with their sheer abundance, could easily account for the observed dark matter density. But how do you find something so elusive? How do you detect a particle that barely interacts with anything at all? This is where the experimental strategies for axions diverge dramatically from those for WIMPs. While WIMP searches typically involve looking for the rare recoil of an atomic nucleus after a collision with a dark matter particle, axion searches often rely on exploiting the axion's ability to convert into photons, particles of light, in the presence of a strong magnetic field. Imagine a giant, powerful magnet, a magnetic field so intense that it can bend space-time itself. Now, imagine that axions are streaming through this magnetic field. Occasionally, one of those axions will interact with the field and transform into a photon, a tiny burst of electromagnetic energy. The trick, of course, is to detect that faint signal, to distinguish it from all the background noise. It is like trying to hear a pin drop in the middle of a rock concert. This is the basic principle behind experiments like the Axion Dark Matter Experiment, or ADMX, at the University of Washington, and other similar experiments around the world. These experiments use incredibly sensitive detectors, cooled to near absolute zero, to search for the faint photons produced by axion conversion. These experiments are pushing the boundaries of technology, exploring uncharted territory in the search for dark matter. But the axion presents a very different type of dark particle possibility. Instead of a massive, weakly interacting particle, it is a light, almost non-interacting particle that could be hiding in plain sight, waiting to be discovered. Could it be that the answer to the dark matter mystery is not a bowling ball, but a feather? Only time and continued experimentation will tell. The search is on, and the universe holds its breath, waiting for us to finally unlock its secrets. But what if these secrets lie not just with WIMPs or axions, but with a whole host of other, less mainstream but still viable dark matter possibilities? The landscape of dark matter research is vast and varied, and the next chapter in this story could reveal even more surprising and unexpected twists. But even with the exquisite theoretical underpinnings and the compelling WIMP miracle, the universe, it seems, is playing coy. Decades of dedicated searches have yet to yield a definitive detection. So what happens when your star player is consistently striking out? Do you bench them, or do you start scouting for new talent? In the world of dark matter research, the answer is a resounding, you diversify. While the WIMP remains a viable contender, scientists have increasingly broadened their horizons, exploring a range of alternative dark matter possibilities, the dark horse candidates waiting in the wings. Perhaps the answer lies with a particle that is neither as heavy nor as interactive as the WIMP, but rather a more elusive cousin of a particle we already know well, the neutrino. Enter the sterile neutrino, a heavier relative of the ghostly neutrinos that stream from the sun and other cosmic sources. Unlike their lighter siblings, sterile neutrinos would not interact with the weak force in the same way, making them even more difficult to detect. Their existence is primarily theorized to explain neutrino oscillations, the phenomenon where neutrinos change flavor as they travel. But could they also be the missing dark matter? The idea is enticing. Sterile neutrinos with masses ranging from a few kilo-electron volts to a few giga-electron volts would interact only through gravity and, potentially, through a very weak mixing with ordinary neutrinos. This feeble interaction would make them incredibly difficult to detect directly, but it would also allow them to decay into ordinary neutrinos and photons, a process that could be detectable by X-ray telescopes. Imagine detecting a faint glow of X-rays emanating from regions where dark matter is expected to be concentrated, a ghostly signal betraying the presence of these elusive particles. Several such signals have been reported over the years, but distinguishing them from more mundane astrophysical sources has proven challenging. The debate continues, but the sterile neutrino remains a contender, a reminder that the answer to the dark matter mystery may lie closer to home than we think. But what if dark matter isn't made up of fundamental particles at all? What if instead it is composed of macroscopic objects, objects far larger than atoms or even molecules? Could the missing mass be hiding in plain sight, not as ghostly particles, but as black holes formed in the very early universe? The idea of primordial black holes as dark matter has experienced a resurgence in recent years. These black holes, unlike those formed from the collapse of massive stars, would have formed in the first fractions of a second after the Big Bang, from the collapse of extremely dense regions of space. Their masses could range from asteroid size to thousands of times the mass of our Sun, potentially spanning an enormous gap in the universe's mass. What makes primordial black holes so intriguing is that they require no new physics beyond what we already know. Black holes exist. We have seen them. The question is simply whether they could have formed in sufficient numbers in the early universe to account for the dark matter. Finding these would be akin to finding a needle in a cosmic haystack. The observational signatures of primordial black holes are varied and subtle. They could be detected through gravitational lensing, as they warp the light from distant stars and quasars. They could also be detected through their gravitational effects on other objects, such as stars and galaxies. And, if they are small enough, they could even be detected through their Hawking radiation, the faint glow of particles emitted by black holes as they slowly evaporate. Imagine detecting a faint gamma ray burst from a black hole that is not much bigger than a pinhead, a ghostly signal from the dawn of time. But what if the dark matter doesn't interact with us through any of the forces we know? What if it exists in a hidden sector, a parallel world of particles and forces that interacts with our own only through the feeblest of connections? This is the premise of hidden sector dark matter, a concept that has gained increasing attention in recent years. The idea is that our standard model of particle physics is not the whole story. There may be other particles and forces out there, hidden from our view because they interact with us only through gravity or some other very weak interaction. These hidden sector particles could be the dark matter, interacting among themselves through their own set of forces, but barely interacting with our world at all. Detecting hidden sector dark matter is an enormous challenge. Because it interacts so weakly with our world, it is incredibly difficult to produce in colliders or to detect directly. However, there are some tantalizing possibilities. If the hidden sector particles are charged under their own set of forces, they could interact with each other through photons, particles of light. These hidden photons could then mix with our ordinary photons, creating a subtle connection between the two worlds. The search is on, and who knows what surprises it may hold. The diversification of dark matter candidates reflects a growing realization that the answer to this cosmic mystery may not be as straightforward as we once thought. The lack of a definitive detection of WIMPs has forced scientists to broaden their horizons, to consider more exotic and unconventional possibilities. The universe, it seems, is a vast and complex place, and the answer to the dark matter mystery may lie in a corner we have not yet explored. One thing is certain: the quest to unravel the nature of dark matter will continue to push the boundaries of our knowledge, to challenge our assumptions, and to reveal new and unexpected truths about the universe we inhabit. But where do you even begin when the possibilities seem endless, when the landscape of dark matter candidates is as vast and varied as the cosmos itself? Despite all our sophisticated telescopes and ingenious theoretical models, the universe's most abundant ingredient, dark matter, remains stubbornly invisible. How then do you hunt something that doesn't want to be found, something that shuns interaction with light and matter alike? The answer, perhaps paradoxically, lies in seeking out the deepest, quietest places on Earth, sanctuaries of scientific pursuit, where researchers are building elaborate traps designed to capture the faintest whisper of dark matter's presence. These aren't your typical laboratories. Forget sterile white walls and gleaming equipment. These are subterranean cathedrals of science, burrowed deep beneath mountains, nestled within active mines, or even submerged beneath vast bodies of water. Why such extreme locations? The answer is cosmic rays. Imagine the Earth constantly bombarded by a rain of high-energy particles from outer space, remnants of supernovae and other violent cosmic events. These cosmic rays can penetrate deep into the Earth's surface, interacting with atoms in the rock and soil, creating a cascade of secondary particles that can mimic the signal of dark matter. To shield their delicate experiments from this constant barrage of cosmic interference, scientists have retreated to the deepest, most isolated places they can find. Think of it as trying to listen for a pin dropping in the middle of a thunderstorm. The deeper you go underground, the quieter it becomes, the better your chances of hearing that faint sound. These underground laboratories are like sensory deprivation chambers for scientific instruments, designed to filter out all the noise and allow the faintest signals to emerge. But simply going underground isn't enough. These experiments require an almost unimaginable level of purity and precision. Every component, every material, every surface must be meticulously screened for even the slightest traces of radioactivity. Why? Because even the tiniest amount of radioactive contamination can produce particles that mimic the signal of dark matter, swamping the detector with background noise. Consider this. Ordinary materials like steel and concrete contain trace amounts of radioactive isotopes, remnants of the Earth's formation. These isotopes decay over time, emitting particles that can interact with the detector. To minimize this background, scientists use only the purest materials, often sourced from remote locations and processed with extreme care. The detectors themselves are often constructed from materials that are naturally low in radioactivity, such as ancient lead, salvaged from sunken Roman ships, or crystals grown deep underground, shielded from cosmic rays. It's like building a house out of only the most pristine materials, carefully selecting each brick and beam to ensure that it is free from any imperfections. The construction of these detectors is a meticulous, painstaking process requiring years of planning and execution. So what are these experiments actually looking for? The basic principle is deceptively simple. Scientists are trying to observe the rare event of a dark matter particle colliding with an atomic nucleus in their detector. Imagine the universe as a vast shooting gallery where dark matter particles are cosmic bullets constantly whizzing through space. Very rarely, one of these bullets might strike an atomic nucleus in our detector, causing it to recoil. This recoil is incredibly subtle, a tiny jolt of energy, barely perceptible. The challenge is to detect this recoil, to distinguish it from all the other sources of background noise that can mimic the signal. Think of it as trying to detect the movement of a single grain of sand on a vast beach. When a dark matter particle strikes an atomic nucleus, the collision can produce several different types of signals. Some detectors are designed to detect the tiny amount of heat generated by the collision, a minuscule increase in temperature that can be measured with extremely sensitive thermometers. Other detectors are designed to detect the faint flash of light produced by the collision, a fleeting burst of photons that can be captured by sensitive light sensors. And still others are designed to detect the ionization produced by the collision, the creation of electrically charged particles that can be detected by electric fields. These experiments are technological marvels, pushing the boundaries of what is possible. They require not only extreme sensitivity and low background, but also sophisticated data analysis techniques to sift through the noise and identify potential dark matter signals. But perhaps the most remarkable aspect of these experiments is the sheer dedication and perseverance of the scientists who build and operate them. These are not quick, easy experiments. They require years of painstaking work, often with no guarantee of success. The search for dark matter is a long game, a marathon, not a sprint. And yet, despite the challenges and the uncertainties, these scientists continue to push forward, driven by a deep curiosity about the universe and a desire to unravel one of its greatest mysteries. It is a dedication that is matched only by the incredible sensitivity of the detectors they craft, and the world is waiting with bated breath to learn what they will find. And yet, despite the incredible lengths to which scientists have gone to create these dark matter traps, the universe has remained stubbornly silent. So, what exactly does the inside of one of these traps look like? How do these technological marvels work, and what makes them so incredibly sensitive? Let's descend into the depths of the Earth to the heart of the search for dark matter. Consider the Xenon experiment, an ambitious project located deep beneath the Gran Sasso mountain in Italy. This detector, like others of its kind, relies on a deceptively simple principle. If dark matter particles are constantly streaming through our galaxy, then occasionally one should collide with a xenon atom in the detector. A xenon employs liquid xenon as its detection medium, a substance that is both dense and extremely pure. The detector itself is a large tank filled with hundreds of kilograms of liquid xenon, shielded from all external radiation by layers of lead, copper, and polyethylene. When a dark matter particle collides with a xenon nucleus, it produces a tiny flash of light and a burst of ionization, a subtle release of electrons. These signals are then detected by an array of extremely sensitive photomultiplier tubes, devices that can amplify even the faintest glimmer of light. The challenge, of course, is to distinguish these signals from the background noise, the constant hum of radioactivity and other sources of interference. To do this, the xenon detector employs a sophisticated technique called time projection chamber technology. This allows scientists to reconstruct the three-dimensional position of each interaction within the xenon and to discriminate between different types of events. Think of it as creating a three-dimensional map of the inside of the detector, allowing scientists to pinpoint the precise location of each potential dark matter interaction. Or journey to the Sanford Underground Research Facility in South Dakota, where you'll find the LUX-LZ experiment, a collaboration combining the legacy of the Large Underground Xenon experiment and the Zeppelin program. This experiment also uses liquid xenon as its detection medium, but on an even grander scale than xenon. LUX-LZ houses a massive tank containing 10 tons of liquid xenon, making it one of the largest dark matter detectors ever built. The experiment is located nearly a mile underground, shielded from cosmic rays by thousands of feet of rock. Inside the detector, liquid xenon is used in a dual-phase time projection chamber. When a dark matter particle interacts with a xenon atom, it produces a tiny flash of light called scintillation, and also knocks loose electrons which drift upwards under an electric field. These electrons then interact with a thin layer of gaseous xenon at the top of the detector, producing a second, brighter flash of light called electroluminescence. By measuring both the initial scintillation flash and the secondary electroluminescence flash, scientists can determine the energy and location of the interaction with extreme precision, allowing them to distinguish dark matter signals from background noise. Imagine this detector as an incredibly sensitive ear, listening for the faintest whisper of dark matter amidst a cacophony of background noise. This vast expanse of liquid xenon, meticulously purified and shielded, represents our best hope of finally hearing that long-awaited signal. Now, cross the Pacific Ocean to China, where the Panda X experiment is underway, located deep beneath the Jinping Mountain. Panda X also uses liquid xenon as its detection medium, but with a focus on even greater purity and sensitivity. The experiment employs a time projection chamber, similar to xenon and LUX-LZ, but with several key improvements. One of the unique features of Panda X is its sophisticated purification system, which continuously removes impurities from the liquid xenon, reducing the background noise to an absolute minimum. This purification system is so effective that the Panda X collaboration has achieved some of the lowest background levels of any dark matter experiment in the world. Imagine this experiment as a pristine sanctuary, carefully guarded against all forms of contamination, a place where the faint whispers of dark matter can be heard with unparalleled clarity. Finally, venture to Canada, where the PICO experiment takes a different approach. Located deep within an active nickel mine in Sudbury, Ontario, PICO uses a bubble chamber to detect dark matter interactions. Unlike liquid xenon detectors, which rely on detecting light or ionization, bubble chambers work by creating a superheated liquid, a liquid that is on the verge of boiling. When a dark matter particle interacts with a nucleus in the liquid, it creates a tiny bubble, a visible sign of the interaction. These bubbles are then captured by cameras, providing a direct image of the dark matter event. It's like photographing a ghost, capturing a fleeting image of something that is otherwise invisible. PICO uses superheated fluid in a unique way that only triggers bubble formation after a very specific energy deposition from a dark matter collision, effectively reducing backgrounds from other types of radiation. Each of these experiments, Xenon, Lux, LZ, Panda X, and PICO, represents a different approach to the same fundamental problem: how to detect the incredibly rare and subtle interactions of dark matter particles. They each use different detector technologies, different shielding techniques, and different data analysis methods. But they all share the same goal: to finally unveil the nature of dark matter, to reveal the hidden skeleton of the universe. But detecting a potential dark matter signal from background noise caused by radioactivity and cosmic rays, the ongoing quest involves building larger, more sensitive detectors deep underground. Yet so far, these searches have yielded null results, placing stringent limits on WIMP properties. Is the universe telling us that our assumptions are wrong? Is dark matter simply more elusive than we ever imagined? Even with these incredible underground sentinels standing guard, patiently awaiting a collision, an interaction, the universe has yet to deliver a conclusive sign. It's a high-stakes game of cosmic hide-and-seek, and dark matter, it seems, is a master of disguise. But what if, instead of waiting for dark matter to come to us, we could seek out its telltale signs in the far reaches of space? What if dark matter, in its elusive dance, leaves behind clues, whispers of its existence that can be detected by instruments far beyond our planet? This is the premise of indirect detection, a strategy that seeks to identify dark matter not through direct collisions but by searching for the products of its annihilation or decay. Think of it as forensic science on a cosmic scale. Instead of looking for the perpetrator, you search for the evidence they leave behind. So what exactly are we looking for? Well, according to many theories, dark matter particles, when they encounter each other in regions of high density, can annihilate, completely destroying each other in a burst of energy. This annihilation process could produce a variety of ordinary particles, including high-energy gamma rays, those incredibly energetic photons, neutrinos, those ghostly subatomic particles that can pass through almost anything, and antimatter particles, like positrons, the antimatter equivalent of electrons, and antiprotons, the antimatter equivalent of protons. It's a process akin to a cosmic self-destruction sequence, a fleeting moment of annihilation that leaves behind a trail of detectable particles. Now, these particles, if they exist, could be detected by telescopes and space-based observatories, instruments specifically designed to capture these high-energy signals from the cosmos. By searching for an excess of these particles from regions where dark matter is expected to accumulate, such as the centers of galaxies or dwarf galaxies, scientists hope to indirectly detect the presence of dark matter. Imagine the galactic center as a dark matter metropolis, a bustling hub where particles are constantly colliding and annihilating, producing a steady stream of detectable signals. It's a challenging undertaking. These signals are often faint and difficult to distinguish from the background noise generated by more conventional astrophysical sources. But the potential reward is immense. An indirect detection of dark matter would not only confirm its existence, but also provide valuable clues about its properties, its mass, its interaction strength, and its annihilation products. One of the key players in this indirect detection search is the Fermi Large Area Telescope, or Fermi LAT, a space-based gamma-ray observatory that has been scanning the skies since 2008. Fermi LAT is designed to detect gamma rays with energies ranging from 20 mega-electron volts to over 300 giga-electron volts, a vast range that encompasses many of the predicted annihilation products of dark matter. Fermi LAT has been used to search for gamma-ray excesses from a variety of dark matter targets, including the galactic center, dwarf galaxies, and galaxy clusters. The galactic center, in particular, has been a focus of intense scrutiny. It's a region known to be teeming with high-energy sources, including supermassive black holes, pulsars, and supernova remnants. But it is also expected to be a region where dark matter is highly concentrated, making it a prime target for indirect detection. Has Fermi LAT found any evidence of dark matter annihilation from the galactic center? The answer is complex. There have been reports of a gamma-ray excess from the galactic center, a signal that cannot be easily explained by conventional astrophysical sources. But whether this excess is actually due to dark matter annihilation is still a matter of debate. Some scientists argue that the excess could be caused by a population of unresolved millisecond pulsars, rapidly rotating neutron stars that emit beams of radio waves and gamma rays. Others suggest that it could be due to some other unknown astrophysical phenomenon. The debate continues, and the true nature of the galactic center gamma-ray excess remains a mystery. Another key instrument in the indirect detection search is the alpha magnetic spectrometer, or AMS, a particle detector that is attached to the International Space Station. AMS is designed to measure the fluxes of cosmic rays, high-energy particles from outer space with unprecedented precision. This includes searching for antimatter particles like positrons and antiprotons, which could be produced by dark matter annihilation. Why antimatter? Well, antimatter is relatively rare in the universe. It is produced in small amounts by conventional astrophysical processes, such as supernova explosions. But if dark matter particles are annihilating, they could produce a significant excess of antimatter particles, a signal that could be detectable by AMS. AMS has detected an excess of positrons in cosmic rays, a result that has generated a great deal of interest in the dark matter community. This positron excess could be due to dark matter annihilation, but it could also be due to other astrophysical sources, such as pulsars. Distinguishing between these two possibilities is a major challenge. Imagine trying to distinguish between the sound of a real fire alarm and a recording of one. Both produce the same sound, but their origins are very different. The key to solving this puzzle lies in measuring the energy spectrum of the positrons, how their abundance varies with energy. If the positron excess is due to dark matter annihilation, the energy spectrum should have a characteristic shape, a cutoff at high energies that is determined by the mass of the dark matter particle. If the positron excess is due to pulsars, the energy spectrum should have a different shape, one that is more consistent with the emission from these objects. AMS continues to collect data, and scientists are working hard to refine their measurements and disentangle the various sources of positrons in cosmic rays. The ultimate goal is to determine whether the positron excess is indeed a sign of dark matter annihilation, or simply another astrophysical puzzle waiting to be solved. The search for dark matter annihilation products is a challenging but potentially rewarding endeavor. It requires sophisticated instruments, careful data analysis, and a deep understanding of astrophysics. But if we are successful, we could not only confirm the existence of dark matter, but also unlock its secrets, revealing its properties and its role in the universe. The cosmos awaits, filled with signals, waiting to be interpreted, and we must continue to listen intently for any message the darkness might send. What new instruments are on the horizon, what innovative techniques are being developed, and how will we forge darkness in the lab? The cosmos, a vast and enigmatic arena, holds its secrets close, whispering them only to those who listen intently. We have journeyed from the deepest terrestrial depths to the farthest reaches of space, seeking the elusive dark matter through direct collision. But what if the nature of this phantom presence is revealed not through a head-on collision, but rather by tracing the echoes of its existence? What if dark matter, in its subtle dance with the universe, leaves behind telltale signs, detectable signatures waiting to be deciphered by the most sensitive instruments ever devised? Enter the realm of indirect detection, a quest to unmask dark matter not by force, but by finesse, by meticulously analyzing the byproducts of its potential self-annihilation. Imagine a cosmic scavenger hunt, where the prize is the identity of the universe's missing mass. What exactly are these cosmic breadcrumbs we seek? According to numerous theories, dark matter particles, upon encountering one another in regions of heightened density, might engage in mutual annihilation, a process where they utterly obliterate each other in a fleeting eruption of energy. This annihilation could, in turn, spawn a cascade of more familiar particles like gamma rays, high-energy photons blazing across the cosmos at the speed of light. Then there are neutrinos, those ghostly subatomic entities famed for their ability to traverse light years of solid matter with impunity. Not to be overlooked are antimatter counterparts like positrons and antiprotons, exotic twins of ordinary matter, rarely encountered under normal circumstances. Each of these could be the telltale sign we've been looking for. The search for these subtle messengers requires a specialized arsenal of telescopes and space-based observatories, instruments meticulously designed to capture high-energy signals from the cosmos. Rather than directly observing dark matter, we are attempting to catch the fleeting remnants of its presence, a cosmic post-explosion analysis, if you will. And where do we focus these instruments? The centers of galaxies, regions brimming with densely packed matter, serve as prime suspects. Dwarf galaxies, small and relatively undisturbed by astrophysical processes, provide pristine environments for dark matter to accumulate. These are the hotspots, the celestial neighborhoods where dark matter annihilation is most likely to occur. But the universe rarely makes things easy. Distinguishing a genuine dark matter signal from the myriad of other astrophysical phenomena presents a formidable challenge. Consider the heart of our own Milky Way galaxy, the galactic center. This region, a mere 27,000 light-years from Earth, is a chaotic cauldron teeming with energetic processes, from the swirling vortex of the supermassive black hole, Sagittarius A star, to the rapid spin of pulsars and the explosive demise of supernovas. Amidst this astrophysical pandemonium, disentangling a dark matter signal becomes an exercise in extreme precision. A gamma-ray excess has indeed been observed emanating from the galactic center, an intriguing anomaly that has sparked intense debate within the scientific community. Is this the long-sought-after signature of dark matter annihilation? Or could it be attributed to a population of yet unresolved millisecond pulsars, or some other exotic astrophysical phenomenon that we are only beginning to understand? Then there's the alpha magnetic spectrometer, a high-energy particle detector stationed aboard the International Space Station. Its purpose, to meticulously catalog the various components of cosmic rays, charged particles hailing from beyond our solar system. Among these components, scientists are particularly interested in antimatter particles, positrons, and antiprotons. These antimatter counterparts are far rarer in the universe, and any surplus of antimatter in cosmic rays could point towards dark matter annihilation. But the universe is a master of deception, and antimatter can also be produced through more conventional astrophysical processes, like the shock waves generated by supernovas. The data gathered from the AMS experiment revealed an intriguing surplus of positrons in cosmic rays, an excess that has fueled speculation of dark matter annihilation. But how do we rule out other contenders? The key lies in scrutinizing the energy spectrum of the observed positrons. If dark matter annihilation is the source, the positron energy spectrum should exhibit a unique fingerprint, a distinctive cutoff at higher energies dictated by the mass of the annihilating dark matter particles. Disentangling these subtle nuances requires innovative and precise measurements to uncover a clear signature. It's a cosmic puzzle demanding the highest level of scrutiny. Confirming a dark matter signal, it turns out, requires eliminating all other possibilities, a task that demands both ingenuity and unrelenting perseverance. It is like searching for a single specific grain of sand amidst a vast and ever-shifting desert. But the quest continues. Gamma-ray telescopes gaze upon the cosmos, neutrino detectors lie in wait, and cosmic ray experiments tirelessly collect data, all in the hope of capturing that elusive whisper from the dark side. Perhaps the next generation of instruments will provide the breakthrough we need. Perhaps a new theoretical insight will illuminate the path forward. One thing is certain. The search for dark matter will continue to push the boundaries of our knowledge, to challenge our assumptions, and to reveal the deepest secrets of the universe. But as these cosmic messengers reach us, we wonder, what will they tell us? What new instruments are on the horizon? What innovative techniques are being developed? And how will we forge darkness in the lab? But what if, instead of waiting patiently for a dark matter particle to stumble into our carefully laid traps, we could actually create them? What if we could somehow summon the shadows, forging darkness itself in the heart of the most powerful machines ever built? It sounds like science fiction, yet this is precisely what physicists are attempting to do at particle colliders like the Large Hadron Collider, the LHC, at CERN near Geneva. Picture this: a gargantuan, circular tunnel, 17 miles in circumference, buried hundreds of feet beneath the Franco-Swiss countryside. Inside, beams of protons are accelerated to nearly the speed of light, then smashed together with unimaginable force. These collisions recreate, for a fleeting instant, the conditions that existed just after the Big Bang, a seething cauldron of energy where new particles can pop into existence. The Large Hadron Collider is more than just a machine. It is a time machine, a window into the universe's infancy. By colliding particles at such high energies, physicists are hoping to produce dark matter particles directly, to pluck them from the quantum foam and bring them into our world. Of course, dark matter, by its very nature, would escape the detector unseen. It wouldn't leave a blip on a screen or a track in a cloud chamber. So how can we possibly know if we have created it? The answer lies in the concept of missing energy. According to the laws of physics, energy and momentum must always be conserved. That is to say, the total energy and momentum of the particles before a collision must equal the total energy and momentum of the particles after the collision. If we carefully measure the energy and momentum of all the visible particles produced in a collision at the Large Hadron Collider, and we find that some energy and momentum are missing, this could be a sign that we have produced something invisible, something that is carrying away that missing energy. Something like dark matter. Imagine you are watching a billiard ball collision. You know the initial speed and direction of the cue ball and the 8-ball. After the collision, you carefully measure the speed and direction of the 8-ball. If you find that the 8-ball is not moving as fast as it should be, based on the initial conditions, you might suspect that something else is carrying away some of the energy. Perhaps a hidden spring in the table, or a mischievous gremlin stealing energy from the balls. In the case of the Large Hadron Collider, that missing energy could be a sign of dark matter. But it is not that simple, of course. There are many other reasons why energy and momentum might appear to be missing in a collision. Neutrinos, those famously elusive particles, can also escape the detector undetected, carrying away energy and momentum. To distinguish a dark matter signal from a neutrino signal, physicists need to look for other clues, other patterns in the data that might betray the presence of dark matter. One promising strategy is to look for events where the missing energy is accompanied by other visible particles, particles that are predicted to be produced alongside dark matter in certain theoretical models. For example, if dark matter particles are produced through the decay of a heavier particle, like one of the superpartners predicted by supersymmetry, Then those heavier particles might also decay into ordinary particles like quarks or leptons, which can be detected by the Large Hadron Collider detectors. It is as if you are searching for a hidden treasure, and you know that the treasure is buried near a specific landmark, like a giant oak tree. The oak tree itself is not the treasure, but it serves as a guide, telling you where to dig. In the case of the Large Hadron Collider, the visible particles are like the oak tree, leading us to the hidden treasure of dark matter. These searches for supersymmetry and other exotic physics are intrinsically linked to the quest for dark matter. Many of the theoretical models that predict the existence of dark matter also predict the existence of other new particles that could be produced at the Large Hadron Collider. By searching for these particles, physicists are not only testing these theoretical models, but also increasing their chances of discovering dark matter. Could the next great breakthrough in dark matter research come not from a telescope peering into the vastness of space, nor from a detector buried deep underground, but from the heart of a particle collider, as matter and antimatter collide, creating fleeting glimpses into the hidden architecture of our reality? The answer remains elusive, but the quest continues, driven by a relentless curiosity and a determination to unlock the secrets of the dark universe. And though the LHC is capable of recreating the universe at its most fundamental level, perhaps the universe has yet to reveal another of its well-kept secrets. And though the LHC is capable of recreating the universe at its most fundamental level, perhaps the universe has yet to reveal another of its well-kept secrets. But what happens when silence becomes deafening, when the most sensitive instruments ever devised come back empty-handed? The persistent lack of a confirmed detection of dark matter despite decades of relentless pursuit has cast a long shadow over the field. This null result is not simply a scientific setback, it is a crisis of confidence. It's a cosmic cliffhanger that has left scientists and theorists alike grappling with a profound question. Have we been looking in the wrong places? Have we been asking the wrong questions? Imagine a detective painstakingly searching a crime scene for clues, meticulously collecting evidence only to find that it all leads to a dead end. This is the reality facing dark matter researchers today. Experiments designed to detect weakly interacting massive particles. The WIMPs, once considered the prime suspect in this cosmic mystery, have consistently failed to yield a positive result. The detectors have become more sensitive, the searches have become more refined, but the elusive dark matter particles continue to evade our grasp. This silence of the labs is putting immense pressure on the most popular models, particularly those based on supersymmetry. Once hailed as the most elegant solution to the dark matter problem, supersymmetry predicts a whole zoo of new particles, including the neutralino, a WIMP that seem to perfectly match the properties of dark matter. But as experiment after experiment has failed to find evidence of these superpartners, the theoretical foundations of supersymmetry have begun to crumble. It's a bit like building a house on quicksand. The structure may look impressive at first, but eventually it will start to sink. The null result from direct detection experiments is not just a challenge to supersymmetry, it is a challenge to the entire WIMP paradigm. For decades, scientists have focused their efforts on searching for particles that interact through the weak force. But what if dark matter interacts through some other force, a force that we have not yet discovered? What if it interacts so feebly that it is practically invisible even to our most sensitive detectors? Perhaps the universe is playing a cosmic joke on us. We have been searching for something that is right under our noses, but because we are looking for it in the wrong way, we cannot see it. These results are forcing theorists and experimentalists to reconsider their assumptions, to reevaluate their strategies, and to explore a wider range of possibilities. Is the WIMP paradigm failing, or are the particles just harder to find than expected? Are we simply not sensitive enough to detect the faint whispers of dark matter? Or is it something far more exotic, something that requires a completely different approach? This ongoing quest for dark matter reminds me of the alchemists from hundreds and hundreds of years ago, tirelessly searching for the philosopher's stone, a mythical substance that could turn lead into gold. They may not have found what they were looking for, but in the process they discovered many other valuable things. Similarly, the search for dark matter may not have yielded a confirmed detection yet, but it has led to countless technological innovations and a deeper understanding of the universe. Perhaps the WIMP is merely a red herring, a distraction from the true nature of dark matter. Maybe it is time to abandon the comfortable assumptions and venture into uncharted territory. Perhaps the answer lies not in a single type of particle, but in a complex mixture of different components, a dark sector as rich and diverse as our own familiar world. Or perhaps the dark matter is not made of particles at all. Maybe instead of trying to catch a dark matter particle, researchers should modify gravity. Are we asking the right questions? Are we even looking in the right place? These questions linger in the silence of the labs, pushing us to examine alternative frameworks that might reshape our cosmic comprehension. And with each experiment and revelation, we find ourselves not at the end, but at a new beginning. The very fabric of the cosmos, woven from gravity and light, seems to demand a hidden ingredient, a shadowy presence we call dark matter. We've chased it across the universe, built elaborate traps to snare it, and even attempted to conjure it into existence within the heart of the world's most powerful machine. Yet, silence. An unsettling, persistent silence that echoes through our labs and reverberates across the vast expanse of space. But what if the solution isn't to seek out something new, some exotic particle lurking in the shadows? What if the problem lies not with what we can't see, but with how we do see? What if our understanding of gravity itself is incomplete? For centuries, we've relied on Newton's law, a bedrock of physics that has guided us to the moon and back, explaining the motion of planets with breathtaking precision. But Newton's theory, while incredibly successful, may not be the whole story. What if gravity behaves differently on the grand scales of galaxies, subtly altering its pull in ways we have yet to fully grasp? Could it be that the missing mass isn't missing at all, but that gravity itself is mimicking its effects? This is the radical proposition put forth by modified Newtonian dynamics, Mondi, a theory that dares to challenge the status quo. Mondi, pronounced like Mondays, was first proposed in 1983 by Israeli physicist Mordechai Milgram. Instead of adding unseen matter to the universe, Milgram suggested a tweak to Newton's law. At extremely low accelerations, far lower than anything we experience on Earth or even in our solar system, gravity deviates from Newton's precise predictions. It gets stronger, pulling with a greater force than expected. This seemingly subtle change has profound implications for the rotation of galaxies. Remember Vera Rubin's groundbreaking observations of flat rotation curves? Mondi offers an alternative explanation. The increased gravitational pull at the outskirts of galaxies could be enough to explain why stars are orbiting faster than they should, without the need for a vast halo of dark matter. Think of it as adjusting the volume knob on a cosmic amplifier. Instead of adding more instruments to the orchestra, which would be akin to adding dark matter, Emond simply turns up the volume on the existing gravitational force, and in many cases it works remarkably well. Mond has achieved considerable success in explaining the observed rotation curves of galaxies, particularly spiral galaxies. In fact, it often does a better job than dark matter models, accurately predicting the detailed shapes of these curves with fewer adjustable parameters. It's as if Mondi has stumbled upon a secret code, a hidden key that unlocks the dynamics of galaxies. But Mondi is not without its challenges. While it elegantly explains galaxy rotation, it struggles to account for other cosmic phenomena. The bullet cluster, that spectacular collision of galaxy clusters we discussed earlier, poses a significant problem for Mond. The separation of normal matter and gravitational lensing in the bullet cluster is difficult to explain without invoking dark matter. Imagine trying to explain why the engine of a train continues moving forward while the boxcars remain behind, using only changes to the train track itself. It is possible, but it requires some pretty elaborate and unlikely modifications. And then there is the cosmic microwave background, the CMB, that faint afterglow of the Big Bang. The tiny temperature fluctuations in the CMB provide a wealth of information about the composition and evolution of the early universe. Cosmological models based on dark matter provide an excellent fit to the observed pattern of CMB fluctuations. MOND, in its original formulation, struggles to reproduce this pattern. Picture the CMB as a complex musical score. The dark matter model can play it perfectly, while MOND struggles with certain passages. To address these challenges, physicists have developed relativistic extensions of MOND, theories that incorporate MOND into Einstein's theory of general relativity. These theories attempt to provide a more complete picture of gravity, one that is consistent with both galactic dynamics and cosmological observations. One such theory is tensor vector scalar gravity, or TVS, developed by Jacob Bekenstein. TVS attempts to reconcile MOND with general relativity, but it's a highly complex theory, and it is still under development. And, to add another layer of complexity, TVS has been challenged by observations of gravitational waves. The debate between dark matter and modified gravity is far from settled. Both approaches have their strengths and weaknesses. Dark matter provides a consistent explanation for a wide range of cosmological phenomena, but its fundamental nature remains a mystery. Modified gravity offers an elegant explanation for galaxy dynamics, but it faces significant challenges in explaining other observations. Perhaps the ultimate answer lies in a combination of both. Perhaps dark matter exists, but its properties are different from what we currently expect. Or perhaps gravity is modified in some subtle way, in addition to the effects of dark matter. The quest for a complete understanding of the universe is a long and winding road filled with unexpected twists and turns. This tug-of-war continues, even as we probe the cosmos with more and more sensitive instruments. Which route will lead to the truth? Only time and more evidence will decide, and perhaps in our relentless pursuit, we might just redefine the laws of the universe. Is it possible that we have been so focused on searching for the missing pieces that we have overlooked a crack in the foundation itself? The pursuit of understanding the cosmos is a relentless dance between observation and theory, a constant questioning of what we think we know. What if dark matter, this invisible architect of the universe, isn't a thing at all? What if it is a symptom of something far more profound, a glitch in our understanding of gravity's fundamental laws? The debate between dark matter and modified gravity is a scientific tug-of-war, a battle between two competing visions of the cosmos. On one side, we have the established order, the standard cosmological model, which posits that dark matter is a real physical substance that interacts primarily through gravity. This model has been remarkably successful in explaining a wide range of observations, from the cosmic microwave background to the large-scale structure of the universe. But it also leaves us with a rather unsettling problem. We have no idea what dark matter actually is. On the other side, we have the rebels, the proponents of modified gravity theories, who dare to question the very foundations of physics. They argue that the observed effects attributed to dark matter are not due to some unseen substance, but rather to a modification of gravity itself. These theories offer an elegant explanation for the rotation of galaxies, but they face significant challenges in explaining other cosmological phenomena. Perhaps you are thinking, could modified gravity theories be reconciled with the evidence from galaxy clusters, gravitational lensing, and the early universe? That is the million-dollar question. Proponents of modified gravity are hard at work trying to incorporate these observations into their models. Some have proposed extensions to modified Newtonian dynamics that can account for the bullet cluster, invoking additional fields or interactions to explain the separation of mass and light. Others are exploring new theories of gravity that can reproduce the observed pattern of fluctuations in the cosmic microwave background. The scientific tension between dark matter and modified gravity is not just an academic exercise. It is a fundamental quest to understand the very nature of gravity, the force that shapes the universe. It is a reminder that even our most cherished theories are subject to revision, that science is a process of constant questioning and refinement. The pursuit of definitive observational tests continues at full speed. As we build more powerful telescopes, delve deeper into the universe, will a new cosmic revelation emerge that validates one approach over the other, or does a more elaborate cosmic tapestry exist? The quest to understand the true nature of the cosmos is ongoing. And who knows? The answer may lie not in one or the other, but in a synthesis of both ideas. The truth as ever, being far more complex and intriguing than we could ever have imagined. And this, without a doubt, is just the beginning of the conversation. The next discovery may just change everything. Even as we probe the cosmos with more and more sensitive instruments, this tug-of-war continues. Which route will lead to the truth? Only time and more evidence will decide, and perhaps, in our relentless pursuit, we might just redefine the laws of the universe. But as scientists debate the fundamental nature of gravity itself, a more fundamental question lingers. How did the galaxies, these cosmic islands of light, even come into being? Were they simply random agglomerations of matter, or was there a grand design at play, an invisible hand guiding their formation? The answer, according to modern cosmology, is that dark matter is the architect of galaxies, the silent builder that shaped the universe as we know it. Imagine the early universe, a mere speck of time after the Big Bang. It was a vastly different place than today, a seething soup of particles and radiation, expanding rapidly and cooling down. Matter wasn't evenly distributed. There were tiny density fluctuations, slight ripples in the cosmic fabric. How did these ripples evolve into the vast structures we see today? The galaxies, clusters, and superclusters that dot the cosmos? The key, it turns out, is dark matter. These dark matter clumps acted as gravitational wells, pulling in surrounding matter like cosmic vacuum cleaners. Normal matter, gas and dust, fell into these wells, drawn by the relentless pull of gravity. As more and more matter accumulated, the density increased, eventually reaching a critical point where stars could begin to form. And this is how galaxies began to take shape. Think of it like water flowing down a mountain. The water follows the path of least resistance, carving out valleys and rivers as it flows. Dark matter acted like those valleys, guiding the flow of matter and shaping the landscape of the universe. Without these dark matter gravitational wells, galaxies would simply not have formed. The universe would have remained a relatively smooth, featureless expanse, devoid of the complex structures we see all around us. But how can we be so sure that dark matter played such a crucial role in galaxy formation? The answer lies in computer simulations, elaborate models that simulate the evolution of the universe from its earliest moments to the present day. These simulations, powered by some of the world's most powerful supercomputers, incorporate all the known laws of physics, including gravity, electromagnetism, and the interactions of subatomic particles. And crucially, they include dark matter. These aren't just back-of-the-envelope calculations. They are sophisticated virtual universes, meticulously crafted to mimic the real thing. What the simulations show is that when dark matter is included, they accurately reproduce the observed distribution and properties of galaxies across cosmic time. Galaxies form within dark matter halos, vast spheres of unseen mass that surround and permeate the luminous matter. These halos provide the gravitational scaffolding that holds galaxies together, preventing them from flying apart. The simulations also show that the properties of galaxies are closely linked to the properties of their dark matter halos. The mass of the halo determines the size and luminosity of the galaxy that forms within it. The shape of the halo influences the shape of the galaxy. It's a complex interplay, a delicate dance between dark matter and normal matter that shapes the destiny of galaxies. Without dark matter, these simulations simply fail. Galaxies form too slowly, they are too small, and they are too randomly distributed. It is a cosmic jigsaw puzzle, and dark matter is the key piece that makes everything fit. Have you ever wondered why galaxies come in so many different shapes and sizes? Why are some galaxies spiral-shaped with swirling arms of stars and gas? Why are others elliptical, smooth, and featureless? The answer, in part, lies in the complex interactions between galaxies and their dark matter halos. When galaxies collide, their dark matter halos merge, creating a larger halo that can influence the shape and evolution of the resulting galaxy. Think of it like a cosmic sculpting process, where gravity and dark matter are the tools that shape the galaxies. It is as if dark matter is the canvas upon which the universe is painted, the invisible backdrop against which the drama of galaxy formation unfolds. But this is not a passive backdrop. It is an active participant, shaping the evolution of galaxies from their earliest moments to the present day. So, the next time you gaze upon a galaxy, remember that you are only seeing a small part of the story. You are seeing the luminous matter, the stars, the gas, the dust, but behind it all, unseen but ever present, is dark matter, the architect of galaxies, the silent builder that shaped the cosmos. And as the galaxies spin and swirl in the void, we wonder, what is the final destination, and when will this intricate cosmic dance conclude? So, we've established dark matter as the architect, the scaffolding, the silent hand-shaping galaxies across the vast cosmic canvas. But the story doesn't end with their formation. It's merely the opening act of a grand cosmic drama, a drama whose final scene is still shrouded in mystery. What if I told you that understanding this elusive dark matter is not just about understanding where we came from, but also about understanding where we are going? What if it holds the key to unlocking the ultimate fate of the universe itself? As the dominant mass component, dark matter exerts a gravitational influence that far outweighs anything we can see. It's the invisible puppeteer, pulling the strings of space and time. Its gravitational pull dictates the expansion rate of the universe, the very rhythm of cosmic evolution. But here's the twist. The expansion isn't constant. It's accelerating, driven by a mysterious force known as dark energy. Dark energy, even more enigmatic than dark matter, makes up nearly 70% of the universe's total energy density. While dark matter pulls things together, dark energy pushes them apart. It's a cosmic tug-of-war, a battle between gravity and this repulsive force. And the balance between these two dark components, dark matter and dark energy, holds the key to the universe's ultimate destiny. Consider for a moment the sheer audacity of this statement. The fate of everything we know and love, every star, every galaxy, every planet, every human being, hinges on the delicate balance between two forces we barely understand. It's a humbling thought, a reminder of our place in the grand cosmic scheme. But what are the possible outcomes of this cosmic tug-of-war? What are the potential endings to the universe's story? One possibility is the Big Rip, a scenario where dark energy becomes so dominant that it overcomes gravity entirely. In this scenario, the expansion of the universe accelerates without bound, tearing apart galaxies, stars, planets, and ultimately, even atoms themselves. It is a cataclysmic end, a universe ripped to shreds by an unstoppable force. Imagine the universe as a rubber band stretched to its breaking point, a point beyond which nothing can hold together. Another possibility is the Big Freeze, also known as the heat death of the universe. In this scenario, dark energy continues to dominate, but at a slower, more controlled pace. The universe expands forever, but at a gradually decreasing rate. Galaxies drift further and further apart, stars burn out, and the universe becomes increasingly cold and empty. It's a less violent end than the Big Rip, but perhaps even more bleak, a slow fade into oblivion. Picture the universe as a dying ember, slowly cooling and fading until it flickers out entirely. A third possibility, though increasingly unlikely based on current observations, is the Big Crunch. In this scenario, dark energy eventually weakens and gravity takes over. The expansion of the universe slows down, stops, and then reverses. The universe begins to contract, pulling everything back together in a fiery implosion. It's the cosmic equivalent of inhaling after exhaling, an idea that captivated even the great Albert Einstein early in his career. Imagine the universe as a balloon that has been slowly inflating. But then it is punctured and all the air rushes out, causing it to collapse. Which of these scenarios will ultimately prevail? The answer depends on the precise nature of dark matter and dark energy, their properties and their interactions. If dark matter is made up of heavy, weakly interacting particles, as some theories suggest, it could eventually collapse into supermassive black holes, altering the geometry of space-time and potentially influencing the expansion rate of the universe. If dark energy is a constant force, a cosmological constant, as Einstein once proposed, the universe will likely continue to expand forever, leading to either the Big Rip or the Big Freeze. But if dark energy is dynamic, if its strength changes over time, the future is far less certain. The universe's fate, it seems, is not written in stone. It is a constantly evolving story, shaped by the interplay of forces we are only beginning to understand. Understanding dark matter is therefore not just about understanding the past. It is about understanding the future, about peering into the cosmic crystal ball and glimpsing the universe's ultimate destiny. Consider the words of the late Stephen Hawking, one of the most brilliant minds of our time. He once said, "The greatest enemy of knowledge is not ignorance, it is the illusion of knowledge." We may think we know a lot about the universe, but the truth is, we are only scratching the surface. The mysteries of dark matter and dark energy remind us of the vastness of the unknown, the immensity of the challenges that lie ahead. The search to understand the universe continues, but what tools will guide us on this quest? And how will we ultimately unveil the universe's invisible skeleton? As we stand on the precipice of the unknown, dwarfed by the sheer scale of cosmic mysteries, one thing is clear. The quest to unravel the universe's deepest secrets demands new tools, new perspectives, and a relentless spirit of innovation. Are we perhaps on the verge of a revolution in our understanding of the dark universe, a revolution driven by a new generation of telescopes and experiments poised to illuminate the shadows like never before? Imagine a world where the invisible becomes visible, where the vast, unseen skeleton of the universe is finally revealed in all its glory. This is the promise held by observatories like the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, or LSST, a groundbreaking facility set to revolutionize our understanding of dark matter and the cosmos. With its unprecedented wide field view and its ability to rapidly survey the entire sky, the Vera C. Rubin Observatory will embark on a 10-year mission to map the distribution of dark matter with breathtaking precision. Think of it as a cosmic census taker, meticulously cataloging the positions and properties of billions of galaxies, all in the name of unveiling the universe's hidden architecture. But how will it achieve this remarkable feat? The answer lies in the phenomenon we've discussed before: gravitational lensing. By carefully measuring the subtle distortions of light from distant galaxies caused by the gravity of intervening dark matter, the Vera C. Rubin Observatory will create a three-dimensional map of the dark matter distribution on a scale never before imagined. This map will not only reveal the location of dark matter, but also provide clues about its properties, its density, and its relationship to the visible universe. Imagine creating a blueprint of a hidden city by studying the way its gravity bends the light of distant stars, a cosmic cartographer charting the invisible. Then there's the Euclid Space Telescope, a European Space Agency mission designed to explore the dark universe and unlock the secrets of dark matter and dark energy. Euclid, slated to launch in the coming years, will employ a different approach than the Vera C. Rubin Observatory, focusing on measuring the shapes and distances of billions of galaxies with unprecedented accuracy. By combining these measurements with observations of the cosmic microwave background, Euclid will create a comprehensive map of the large-scale structure of the universe, revealing how dark matter has shaped the cosmos over billions of years. It's like creating a three-dimensional model of the universe, a virtual reality tour of the dark side. And let's not forget the Nancy Grace Roman Space Telescope, formerly known as the Wide Field Infrared Survey Telescope, or WFIRST, a NASA mission designed to probe the mysteries of dark energy and dark matter. The Roman Space Telescope, named in honor of NASA's first chief astronomer, Nancy Grace Roman, will feature a wide-field instrument that will allow it to survey vast swaths of the sky with exceptional sensitivity. With its unparalleled infrared vision, the Roman Space Telescope will be able to peer through the dust and gas that obscure our view of the distant universe, revealing galaxies and structures that are otherwise hidden from view. But this isn't only about bigger telescopes. The ingenuity of scientists is also on display to the world. Direct detection experiments are constantly pushing sensitivity boundaries for a wider range of candidates. While some continue to seek out the faintest collision with ever-increasing precision, others are looking for completely different signals, perhaps ones born from entirely new theoretical frameworks. It's not unlike casting a wider net, or perhaps designing an entirely new kind of net altogether. Imagine a symphony orchestra tuning up, each instrument preparing to play its part in a grand cosmic composition. The Vera C. Rubin Observatory, Euclid, and the Nancy Grace Roman Space Telescope are just a few of the instruments in this orchestra, each designed to play a unique role in unveiling the universe's invisible skeleton. As these instruments come online, and as new experiments push the boundaries of what is possible, we can expect a flood of new data, new discoveries, and new insights into the nature of dark matter. Will we finally identify the particles that make up this elusive substance? Will we discover new forces or interactions that govern its behavior? Will we rewrite the textbooks of cosmology and particle physics? The answers, as always, lie hidden in the darkness, waiting to be revealed. But the tools are ready, the minds are sharp, and the quest continues, and there are always new secrets hidden in the cosmos. Is it possible that the answer was right in front of us the entire time? That all of our greatest minds have simply been looking in the wrong direction all along? As we journey to the outer limits of what is known, and what we believe we know to be true, we find that the deeper our search, the more endless the mystery seems to become. For all of our searching, our discoveries, and the theoretical constructs that we have created along the way, dark matter remains one of the most significant unsolved puzzles in modern science. The evidence for its existence is frankly overwhelming. From Fritz Zwicky's initial observations of the Coma cluster to the work of Vera Rubin and her colleagues on galaxy rotation curves to the incredible mapping of the cosmic microwave background, everything that we know about the universe tells us that dark matter is there. Its invisible hand is at play in everything that we see. However, its fundamental nature is still shrouded in complete darkness. We know that it is there, we know that it is exerting its influence, but what is it? Is it a particle? Is it an exotic state of matter? Is it a modification of gravity? The search to define the composition of this phantom universe has pushed the boundaries of particle physics and cosmology. The instruments that we create become more and more sensitive. The mathematical and theoretical equations become more elaborate and complex. Every attempt to understand is met with an equal and opposite reaction of complexity. From the deepest mines on planet Earth to the most sensitive detectors on the International Space Station, our quest to identify this invisible skeleton continues. Are we close to a breakthrough? Are we on the verge of cracking the code to this cosmic riddle? Many scientists believe that we are. With each new experiment, with each new observation, with each new theoretical insight, we inch ever closer to a full understanding. The story of dark matter is one of incredible scientific ingenuity, of remarkable technological innovation, and of unwavering human perseverance. It is a story that embodies our persistent drive to explore the unknown, to push the limits of what is possible, and to understand our place in the cosmos. The quest to identify this invisible skeleton is a beacon for the future of scientific innovation, promising potential breakthroughs that could revolutionize our understanding of the cosmos. The stakes are high, the challenges are immense, and the answers remain elusive. But if humanity is to unlock the secrets of the universe, there is no turning back from the search. Perhaps the greatest testament to this quest is that it embodies the persistent human drive to explore the unknown. From the first humans who looked up at the stars and wondered what they were, to the scientists who are today building the most sensitive dark matter detectors ever conceived, humanity has always been driven by a desire to understand the universe and our place within it. It is this innate curiosity that will ultimately lead us to unravel the mystery of dark matter, no matter how long it takes. Consider the words of Neil Armstrong, the first human to walk on the moon. In the year 1969, as he took that first step onto the lunar surface, he spoke the famous words, "That's one small step for man, one giant leap for mankind." Those words encapsulate the spirit of exploration that drives us all. The search for dark matter is another giant leap for mankind, a quest that will challenge our understanding of the universe and ultimately reveal new truths about our place within it. But what will we see when the invisible becomes visible? Only time and tide will tell if the universe is ready to reveal its ultimate secret to us, or whether it will continue to tease and tantalize with its cosmic trickery, even as we continue to search for its long-lost dark matter.